joined as a postdoc in ISAR Thiruvananthapuram, and now currently he is affiliated in Esenberg National Center for Basic Sciences and doing his postdoc. So his research interest is quantum thermodynamics, quantum information theory, quantum foundations, and quantum entanglement theory. So today he is going to talk about thermodynamic signatures of quantum entanglement. So Mirda, now the stage is yours.
Oh, thank you, Sumit, for a nice introduction. And I really appreciate the effort you all people are giving to organizing such a nice and wonderful event for a long time, from 8 May to 16 June. So it is quite a long time and I know how much effort you have to give to organize such a wonderful event. So so today, good morning, everyone. So today I'm going to talk about this thermodynamic signature of quantum entanglement, basically the connections between thermodynamic properties and what is the reflection of those properties in quantum entanglement. So my talk basically focused on these three works that I have done in my PhD and the postdoc. So the first work I did with my supervisor, Professor QIQT23, and Dr. Tomal Guho, who is my collaborator. He is now right now in Hong Kong. The second work, the PRL one, I did with Dr. Manik Banit, my mentor, postdoc mentor, and Shamgit is a BSMS project student. And the last work we did very recently and put it in archive with our experimental group, ISAR Pune experimental group, Professor T.S. Mohes and the PhD student Jitendra Joshi. So this is my plan of talks. First, I will discuss the work extraction from an isolated quantum system, the analogous to adiabatic process. And then those work is called ergotopic work. And then I'll try to make a connection between this ergotopic work and the quantum correlations, more precisely quantum entanglement. And then I will summarize. So let me introduce the adiabatic process. Already we all know what adiabatic process is. It is something that it cannot take heat from outside. It cannot give it back to the outside. So now if we want to extract work from from a system which governs through an adiabatic process, what happens? The system's energy acts as a fuel. So if you get some work from an adiabatic system, that means your system's energy get decreased, and that energy comes as a work. Now, if you put some energy into that systems, then eventually system's energy will be more. So that is the main process. So then the simple question is, what is the analogous description of these things in quantum mechanics or quantum systems? So you see that quantum systems, again, isolated means I have to study the closed systems where the system is not interacting with your environment. It is not at all interacting. So when you're taking the system is isolated and closed systems, what is the operations? The only valid operation is the unitary operations. So then if you want to extract work, maximally from a quantum system, how much work you can extract from that systems, that would be characterized only by the unitary operations. So that means how much energy, so if your initial state has this much energy, so after applying unitary operations, that is the only valid operations, how much energy you can decrease into the final systems. So that's why only evolution. So to do that, we can actually give some external potential or field to apply all possible unitary. And so that is the maximum extractable work. You see in this quantity, so it is the energy difference, energy of the initial system and energy of the final systems. Rho tau is the after unitary evolutions. So I did a minimization over unitary because I want to reach to the lowest energetic state. In general, unitary can actually heat up your state, not heat up, increase its energy. So, but our task is to extract work. So I have to go to the lowest energetic states. So I have to choose a proper unitary for the given state so that it goes to the lowest energetic states, and that state sometimes is called passive states. So let's understand these things more precisely. What happens? So since we are doing unitary operations only, what happens? Only the spectral things so the spectral things would remain same, only the basis would change, right? So if you take a state, initial state, which is in spectral form, this is the spectral decomposition of that state. We all know the spectral decompositions. So then the passive states would be this form, which means your lowest energetic state have the highest probability occupations, and highest energetic state would be the lowest probability occupations. So that is the form of a passive state. This type of state would actually take the lowest energetic state under the unitary operations over all this, over this row. So look into this passive state very carefully. This state is a diagonal in energy basis. So that is the first property. So if you, now the second thing is that if you know the state is a passive state, you don't require full tomography to know that states. You only need a diagonal tomography, right? So these two properties quite important, and that can be useful later. Okay. So let me share what happens if we take not a single system, rather a bipartite system. Since we are actually study the correlations, we have to take the bipartite systems. So you say, if we take a bipartite system, then what happens? I am motivated to extract work from that bipartite systems. What I can do, I can construct a different configurations. Like I can probe that systems totally, I mean go overally. I mean these two party can actually probe the systems globally and try to extract energy and store it in quantum battery. Then they can do something else also. They can actually do extract work locally and try to store it. But you understand, the only operation is a unitary. Obviously, the global unitary operations, that set is the larger than the local unitary set. So obviously, this is the global ergotropic work and this is the local ergotropic work. It is very obvious that the ergotropic gap would be always greater than 0. So that is the main point, that this ergotropic gap is increasing, and that in that part, this quantity we'll call collaborative advantage of ergotropic gap. We'll sometimes call ergotropic gap. And this is the major quantity that will be useful to study the correlations, I mean, to study the entanglement. So this part is quite important. So then what happens? Let's see how this can be useful to extract work, I mean, to study the correlations. So let me take some Hamiltonian. Let me take the Hamiltonian is in this form, which is the linear space Hamiltonian. It can be generalized, but it is not required right now to understand these things. So if you have some state which is a pure product state, what will happen? Look in the example 1, the state is a product state and a pure product state. Then we can show this ergotropic gap is 0. There is no collaborative advantage. Whatever they can do globally, they actually can do locally. But if they start with some maximally entangled state or any entangled state, then what will happen? This gap will be non-zero. And that is the interesting part. So that means at least for the pure product state and pure entangled states, I can look into the gap and say if it is 0, then it is a separable form. If it is a not 0, then it is an entangled. But that comment is only valid for the pure states. Now, so that means then the question is why this is coming, why this is non-zero. One thing is that earlier we said that collaborative advantage is coming because of the global unitary operations, but it is not only that. This is coming because of the entanglement even. Because here also the global operation was there, but here also the global operations I have taken. But the entanglement correlations between the system, that is quite useful to get this collaborative advantage. So let's move to the next. Okay, then the question is, can there be some collaborative advantage for the separable kind of states? Because we want to study the entanglement, then I have to make a demarcations between the separable and entanglement, right? Then I don't mean it should not be good to bound only for the pure states. I have to consider the mixed state, and then I have to make a demarcations between the separable state and entangled states. And unfortunately, whether I should say unfortunately or not, but unfortunately this gap becomes not is equal to 0 for the separable state also. I mean for the mixed separable state, right? But then the question is, for the mixed separable state is also not is equal to 0. Then the immediate question is, can this gap this gap can be higher for the entangled state and lower for the separable states. Actually, that is true. So what we have done, we took all separable state, bipartite separable state, any D1 cross D2 systems, and try to find out what is the maximum gap, maximum collaborative advantage, and we find a bound that the maximal collaborative advantage is this much. I mean, this quantity, you don't need to bother about this quantity, but this is a dimension dependent and a Hamiltonian dependent quantity. So this, for the separable state, we can get a upper bound or threshold. Now, if I give you unknown quantum states and you suppose perform experiment and try to find out the ergotopic work, global work and local work, and if you see that their difference or collaborative advantage cross that bound, then what it is, why it is coming? Okay, this is coming because they are not separable, because they are, these two parties are somehow connected, I mean, some peculiarly connected. Entanglement type of correlation exists. That's why it is, that's why this bound, that's why the collaborative advantage is exceeding. So that is the main power. So it is a very, we are very lucky, and that we find that advantage. And you see, this advantage is thermodynamic advantage. I mean, some advantage, some quantity which is actually very useful for quantum battery. So that is the main, one of our main part of the first work, that we find out a threshold value for the separable states. Now, how much region it can actually capture? So let's try to understand for this particular type of states, Warner states. I have taken 2 cross 2 systems. So we know that the Warner state from other different criteria, we know that the state is separable for 1/3 and half, 1/3 and below this region, and state is entangled remain greater than 1/3 region. So now, suppose, so for the Warner state, we know this result from PPT criteria or some other criteria also, reduction criteria. So let's check how beautiful this criteria is, how much entanglement it can capture for this kind of states. So if I told you that I am giving you a state and tell me whether the state is entangled or not, and you are bound to do this ergotopic type of measure. So if I don't give you any further information what the state is, I mean, what is the spectral, you understand, you know this thing, that spectral information is not sufficient to say whether the state is entangled or not. A separable state and a entangled states both have the same spectral, but their properties are different. One is entangled, one is separable. So that is, spectral information is not sufficient always. So if I give you a state, that might be anything. Now, you check the collaborative advantage when this, and if you find out the value is greater than half. So right now I'm talking about for the 2 cross 2 systems. So if you find out the collaborative advantage is greater than half, then you can immediately say that the state is entangled, because the threshold bound for the separable, unknown separable state is half. But can we improve that bound? Suppose you know the spectral. Suppose when I'm producing you a separable state, when you are producing Warner states, so you know what is the Warner states and you know the spectral of the Warner states. Then actually you can improve the threshold value for the separable states, and you can, using this our criteria, we can go up to 1/3, and so we can actually completely characterize the Warner states, entanglement of a Warner states with our thermodynamic criteria. And one important thing, our thermodynamic criteria okay, we know some entanglement measure like von Neumann entropy, but our criteria is energy dependent criteria, so that can be quite useful in experiment. Okay, because every time we deal with Hamiltonian, so that Hamiltonian provides you the energy, so it might be easy. Sometimes it might be easy to detect entanglement through our criteria. So then what we did, we actually performed an experiment with this Isar Pune group, and we took NMR architecture, where we took Hamilton, we took our systems, homonuclear systems, hydrogen, and first we create an entanglement. They are actually governing with this Hamiltonian, and this hydrogen, these molecules, actually we prepared a first we prepare a Warner state between these two, This is the process of one state. This can be discussed later. And then what we did, we actually transform this state to its passive state to find out this ergotropic gap quantity. And then we experimentally calculate those ergotropic things. And then we actually have seen this blue line is the theoretical bound theoretical ergotropic gap. And this pink circle as the experimental value. And this one, then what we plot state independent bound, this one, which is actually touching 0.5. So state independent bound, state independent threshold value is actually capturing greater than half, and state dependent, global spectral dependent bound actually capturing greater than 1/3. So so that is the first experiment we did. Then let me come to the multipartite case, whether our criteria can detect entanglement between the multipartite or many body systems. So so we know that many bodies, if you consider many body systems or multi-party systems, then their entanglement can be a different class. That class can be very peculiar even. There can exist some, if the systems are actually qubit system, the entanglement can be GHZ kind of entanglement, W kind of entanglement. There can be some biseparable states. There can be some fully separable states. And we know that from lower to upper direction, this direction is not possible under local operation and classical communications. So that implies there exists some different kind of entanglement, the classification of entanglement is different. And even not only that, if you consider GHZ state and W states, then their entanglement is also very different. So let me go very quickly. So in that scenario, when you consider multipartite scenario, there also you can actually extract work very different way. You understand ABC pictures where the parties are actually extracting work in a different configurations, and you understand this C part has the more extractable work than A part and B part, and B part has the less extractable work. I mean, ergotropic advantage. Then we did then actually in the multipartite systems, we did the experiment, and we considered a 3-qubit system and 10-qubit systems, and see a very good result there for the GHZ kind. So we did this experiment to prepare some GHZ kind of mixed states, and it actually completely characterized the many body systems entanglement under different division, different partition. Now let me talk about the genuine entanglement. Okay, these results are the entanglement of a bipartite kind of entanglement. It's not a genuine kind of entanglement. But now I'm going to talk about the genuine entanglement measure. So can our measure is a good candidate to capture genuine entanglement? We'll say yes for the pure states. For the mixed state, the study, not our study only, I mean, for the mixed state, we know very less good entanglement measure. So a genuine entanglement measure, what it should be? It should give you non-zero value only for the genuine entanglement state, but for the biseparable and for the fully separable state, it must give you 0 value. Okay, so we actually, I told you earlier that the bipartite ergotropic gap actually plays the major role everywhere. So actually here also I defined a quantity which is a minimization over all bipartition. So if you see, so this value, we'll just see that for the genuine entangled state, this value would give you non-zero, but for all other cases like fully separable or biseparable cases, this would give you 0. And you can see that for the product states, this is 0. For the biseparable state also, the minimum of these 3 quantities are actually those bipartite ergotropic gap. This is 0. Only for the genuine entangled state and some W states, those are tribal and extended GHZ states, this becomes non-zero. And I was talking about whether it can make a distinction between GHZ and W states or not. You look here for the genuine GHZ type of state, these values are same, all are equal. But for the tribal or extended GHZ, which is the Warner kind, these values are different. So this actually saying that for the GHZ and W, looking into this fact, we can actually distinguish between GHZ and W kind. states also. Then actually we not only stop
Mirza,
here.
we have
Yeah.
5 more minutes.
I will take 2 minutes, 2-minute more.
Okay.
So first we defined this quantity, which is the genuine measure. Then we come up to okay. Then the question is, I was talking about the pure states only, right? And then what about the mixed states? So mixed state easily you can generalize for the convex loop optimization, but that is not very useful. That would lose its physical meaning. And I personally don't like this type of measure, but okay, it can be. In literature, many people use these things, but it is not easily calculatable. So, but this measure, this genuine measure, is actually related with the concurrence measure, but it is not same. This is related with this function. And then we come up to some other measure also, like average, ergotrophic gap. Those are all the function of this quantity. Then ergotrophic field and ergotrophic volume. Then one may ask why this different measures is required. When you are giving one measure, why you are required different measure? For that, to understand that things, I have to spend a few minutes. So the entanglement state transformation is a very difficult problem. I mean, because if I give you two states, two entangles, psi and phi, whether this is for a bipartite system, this is quite easy. Let's talk about only pure entangled state. Bipartite system, why it is easy? Because we have a Nielsen-Kempe criteria. I'll check a Nielsen-Kempe criteria and make a precise comment on whether from this state to this state is possible or not. But what about the multipartite entangled states? There is no such a very general results about the transformation between two multipartite entangled states. So if there is a no, then what we can do, one can actually check all possible LOCC operation and check whether this is possible or not, this transformation is possible or not. And that is quite complicated task, because the LOCC operations, their characterization is not very easy. Their set is not very good and mathematically characterizable set. So then people can take a different approach also, like entanglement quantifier. So if from a state psi to phi LOCC transformation is possible, then psi to phi set, I said psi to phi, then obviously psi has a more entanglement than phi. That is the general definition of an entanglement measure. Then every entanglement measure must satisfy these conditions. But when the two states are not LOCC connected, their entanglement measure value can be different. I mean, suppose you have a two entanglement measure E1 and measure 1 and measure 2, it might happen when the two states are not connected under LOCC. M1 measure can favor psi, M2 measure can favor psi. Favor psi means M1 measure can give a higher value for psi, M2 measure can give higher value for phi. So if these type of things happen, if you find a two measure, and if you ask you to this question that you have a two given states, can you make any comment the transformation directions? Then if you have an independent measure, then you can check their entanglement, and if you find a different order, then you can surely comment that this transformation is not possible. So we have shown the few examples that these two. Let's talk about these two states, phi ABC and chi ABC. Whether this transformation, this state can be transferable from one to another under LOCC operation or not. The answer can be given from here. So this is one monotone which is saying that the second state is better than the first state, but this is another monotone which is saying the first state is better than the second one. So this different order means they are not LOCC transferable under deterministically LOCC is not transferable. So that's all. Let me summarize these things. So what we did first, we first provided energy dependent measure, which is independent than the von Neumann entropy measure. Let me clarify these things. It is an independent measure than the von Neumann entropy, and it is necessary sufficient for the pure entangled states. Not only that, it can detect entanglement when no information of the state is available. I mean, you don't have any information, but still you can actually detect entanglement. If you have information, you can actually get a better range of entanglement, and it captures a big range of entanglement for entangled states. And we are really positive about its experimental realizations. We did experiment on NMR architecture, but in other different quantum architecture also it is possible, because it is the energy dependent measure. And for some class of bipartite mixed states, it provides a necessary and sufficient conditions that I have not mentioned, but you have to look my papers to get that things. And not only bipartite entanglement, it can capture the genuine entanglement even. Yeah. So thank you.
Thank you, Mirda, for such a nice talk.
Yeah.
And so
Sure.
now the stage is open for questions. So participants can themselves unmute themselves and ask question to the speaker.
I have a question.
Yeah, sure.
So, is there any entanglement measure for Gaussian state?
Yeah, people have done some work using the passive state concept, but I don't know those are very well studied. I mean, one can look for those things. I mean, I think it would be quite interesting.
Okay.
I mean, I have not personally, I have not studied it yet, but it is very interesting things. Yeah. And it is very interesting question actually. I mean, one can actually look those systems and try to find out whether the energy measure, this kind of measure can be useful there or not.
Okay. Now they have this separability criteria, but saying that they can be entangled. Like, is that
The separability criteria based on what property they
the EPR variable type variable, like
okay,
that variance using a variance condition delta U square.
Yes.
Suppose U and V are EPR states like variable.
Yes.
And delta U square plus delta V square. That total variance is less than 2 something.
Understood. Those are the well-defined measures for the Gaussian states, but one can look into this quantity, whether this how we can actually apply this thermodynamic measure there. That is a good point. I mean, that we can further explore.
Okay. So there is no as such currently.
Yeah, there is no as such, but people have done some studied on the Gaussian passivity, all those things. You can actually you can find out some literature.
Okay. Thank you.
So any other questions?
Stop share.
So if there is no other question,
yeah,
then we can move to the next speaker. So Mirza, thank you for this talk.
Yeah, thank you. Okay.
So,
I'm leaving. I'm just stop share, right?
Yes, you can stay online.
Yeah, okay.
Okay, so let me now introduce our next speaker, Mr. Ganesh Chandra. He's from HRI. He's doing his PhD from HRI. So his research interest is quantum information and computation, quantum many-body physics, and quantum non-Hermitian quantum physics. So today the title of his talk is Entanglement and Phase Transition in the Long-Range Extended Ising Model. So welcome, Ganesh. So
hello, hi.
You can present your screen.
Yeah, sure. Is it visible?
Yes, absolutely.
Yeah, thank you. Thank you so much for the introduction. And I am genuinely so happy that almost every, this conference basically included almost every quantum researcher in the entirety of the subcontinent. I'm very happy to see such a comprehensive conference that includes almost every, gave opportunity to almost every researcher who's doing research in QIC and its affiliated regions. So saying so, I would like to present this talk based on our recent two papers. One is essentially exploring the properties of long-range extended Ising model. This is in collaboration with Srijan, who's my senior in HRI, and Devashish, who is now a postdoc in Edinburgh, and my advisor Aditi Sen. And just to give you a context, my outline of the talk is going to go like, I'll introduce what is almost everyone I think here would be familiar with the Ising model, but I'll introduce what is the long-range Ising model, long-range extended Ising model, and I'll describe the first paper's result. that is how quantum correlations of finite range can be used to mimic the quantum correlations of a fully connected expensive, I'll define what expensive means, expensive fully connected model. And in the second part, I'll just describe the dynamics of this model, like what happens if we quench between the different phases of this model, which is whose phase diagram is quite rich. And just to give another, I'll start with the static part. To give a shout out, just last night there was a paper in Nature that has shown that this exact the same class, that is a 2D Ising model, has been simulated on an IBM quantum computer, and that has shown results. That has shown that this is a paper that has shown that the dynamics of this model have been simulated on an actual quantum computer, such that the result being that this strong entanglement behavior, which I'm going to talk about, has been simulated, which is inaccessible to many modern tensor network methods. So in that sense, mimicking or trying to establish entanglement properties on real quantum devices is a very relevant problem, and it is essential to find systems which has such entanglement properties, which are in general has been shown to be useful to mimic many important quantum phenomena. Okay, so let me introduce the workhorse of this of our talk, that is the long-range extended Ising model. If you observe carefully, this is the on-site magnetic field. Here, there is, if we ignore this, the middle term, it just looks like sigma x and sigma x n plus r, and r being, if it's just one, it's just nearest neighbor. And if it's if there is one more interaction term that is present, that is the next nearest neighbor is also present, we would see that this model is long range. On the other hand, whenever there is more than one neighbor to interact, it's not just they are interacting directly, but there is a sigma z that is being acted in between in the spins that are present in between. Okay, and in general, these models are observed only in the trapped ion experimental systems, and trapped ion systems have an interaction strength because they are charged ions. They will follow the Coulombic law, and they will fall off as 1 over r power alpha, depending on the kind of interaction. If it's dipole interaction, it will go as alpha 3, and if it's just a single, depending on the multiple expansion that can be utilized, we can show that different alpha values can be engineered to simulate this model. This model, what we consider is that we'll not just consider blindly the fully connected model, that is 1 to n minus 1, that all spins are talking to every other spin. On the other hand, we'll also consider the finitely connected model, where it's not necessary that all the spins are talking to every other spin. Rather, it's enough. We show that it's enough that the system, if it's finitely connected, also the entanglement properties can be mimicked. And this model has transition points in the alpha decay, which I'll call decay rate or alpha interchangeably throughout the talk. It has been shown in this PRL that between 0 and 1, this has something called a non-local phase, and between 1 and 2, it has something called a quasi-local phase. This is the important phase which we'll focus on. And from 2 onwards is essentially, above 2 is essentially local, or it is known as simple, well-known Ising class of model. Okay, and of course, this is Ising class in the thermodynamic limit. Whenever there is finite, it takes a lot of much more stronger alpha to mimic the Ising class of the Hamiltonians. Okay, now these models, these class of models, without the z in between, if there is just blindly 1 over r power alpha sigma x n plus r, These class of Hamiltonians have been experimentally simulated in many works, especially ion trap Hamiltonian, ion trap quantum systems. Like people like Alexei Gorshkov and Christopher Monroe have done many experiments in this direction. I'm just flashing some of them here, and especially this paper. This paper has shown Joseph Wright has shown that what we are talking about, the finite range interaction, is definitely possible on an ion trap system, and especially these are evidences for the fact that these are naturally occurring systems and can be engineered with extremely high precision. And yeah, so the main advantage of this model is that this model is analytically solvable analytically solvable, which was this was initially the method is initially prescribed by LSM, and the method goes like this. It essentially mapped every spin to spinless fermions by a map called Jordan-Wigner transformation, and then the Hamiltonian, the initial Hamiltonian which I have shown, maps to something that is looking like this, where JR is essentially 1 over R power alpha, and this model for the Kinaid looks like the Kitaev long-range model. Although Kitaev long-range model usually has long-range interaction in the superconducting term, what we are considering is that long-range interaction is also present in the hopping term with the same fall off rate. Okay, and so this model, we are not considering in the first part of the talk. I'm not considering the periodic boundary. This is open boundary. So because there is open boundary, we cannot perform the Fourier transform and going to much smaller matrices. Rather, we have to deal with n cross n, that is number of particles cross number of particles, rather than number of spins, basically number of spins, n cross n matrices that are in general written like this. This is called the Namu formalism, and the corresponding Aij and Bij look like this. We try to manipulate these Aij and Bij and find the corresponding ground state and perform our calculation. So the model essentially looks like this, in that there are spins that are sitting in the open on a one-dimensional spin chain. Every spin in general is talking to trying to talk with its neighbors being the plural. If it's nearest neighbor, they are just talking to these two are just talking to each other with just one strength of interaction. The next nearest neighbors are talking with 1 by 2 power alpha, and next nearest are talking with interaction 1 by 3 power alpha. This is the setup. What we want to study is the property of entanglement between the nearest neighbors, that is rho 1, 2. I'm just calling it as rho 1. And between rho 1, 3, I'm calling it as rho 2. It's not. I'm not saying that there is translational invariance, because there is no translational invariance. But this is just the naming convention we have chosen, that if between the first spin and the rest of the system, how is the entanglement decaying down, and what are the corresponding properties of that entanglement? That is the main central theme of our study. Okay, so how do I calculate such entanglement? It involves, I'll just take you, I'll not take you to details, I'll just show the corresponding equations. The same A and B matrices which I have shown just now, these matrices can be used to study get the corresponding ground state using this trick. And if I just solve the corresponding A plus B and A minus B, I'll get the psi t and phi t. Both of them are required, such that I want to calculate the bipartite density matrix of this system. The bipartite density matrix has in general and such a SU2 decomposition. And that looks like this. And if we just find out these elements, that is mz and the corresponding cxx, cyy, and czz, the other elements mx, my, and other cross correlations go to 0 because of the Hamiltonian properties. You can look up the details in the paper of why they go to 0. And we calculate these elements by using something called the Toeplitz matrix. The Toeplitz matrix can be constructed by considering this G, which is colloquially some form of a Green's function matrix. It's not necessarily, but it's just it looks like that we are taking one state of the system to the other state of the system, and we can take this and calculate the CXX, CYY, and CZZ that is looking like this. Once we have done this, and we can now calculate the main quantity of interest, that is the entanglement between R. If you remember, R is just this R. This is R equal to 1 and R equal to 2. So entanglement between first two spins, entanglement between the first and the third spin, entanglement between first and the fourth spin. As such, we calculate entanglement versus R. So this is what we want to study. Now, this is the main result. Is that if I calculate the entanglement for n equal to 256, that is, there are 256 number of spins, and if we look at z equal to 255, that means, remember, z is essentially like the coordination number. That means the model is fully connected. The Hamiltonian is fully connected, and this entanglement pattern decays down looking like this. Okay. On the other hand, if we just consider 5 interactions between just the first and the 6th spin as the maximum amount of interaction, or first and the 11th spin as a maximum amount of interaction, or as such, if we just consider minimal interaction that is present in the system, that corresponding Hamiltonian also mimics the same behavior of a system that is fully connected. This is only possible in the quasi-local regime of the alpha, which is what I have shown before, is that when alpha is between 1 and 2 only, then the model has this property, in that it can mimic the properties of a fully connected system by finite connection range. Okay, that is, entanglement pattern of z equal to 55 is mimicked by z of the order of 10. Now we further go on to show it's not even necessary to connect these many spins. If we just decrease the if we decrease the amount of alpha, that is, strengthen the interaction between these spins, the corresponding z equal to n-1, that is the black boxes, this behavior can be simulated by even z equal to 4 by an alpha equal to 0.9. But for alpha equal to 1.5 and fully connected model, the corresponding behavior of this Hamiltonian, the entanglement behavior of this Hamiltonian, can be mimicked by z equal to 4 and alpha equal to 0.9. This is quite useful in the sense that in general, whenever there is a quantum approximation and optimization algorithms are applied on a superconducting platform, in order to simulate, let's suppose, in order to simulate the ground, in order to find the ground state of such a Hamiltonian, such a similarly connected Hamiltonian on a superconducting platform, it is in general required to make order of n factorial connections between all such spins. If the model is fully connected, it would require order of that n equal to 255 and its corresponding factorial number of connections that are required, and these many number of gates. It is well known that if you increase the number of connections, or if you increase the depth of the circuit, errors keep piling up, and it is very hard to simulate to get out any meaningful result on such a platform. On the other hand, if you can reduce somehow reduce the number of connections between the corresponding spins, then there will be a reduction in noise, but you will not lose out on any entanglement properties, as we have shown below, if one is restricted to study the model, that is study the behavior of the model between alpha 1 and 2. So this is basically the main result of the first paper. And this is although we have showed for alpha, we have shown for alpha between for any given alpha, this kind of a behavior could be mimicked. Just alpha equal to 0, that is fully connected with every other spin is talking to every other spin with the same strength, has always been shown before by this group on how to use chimera qubit connectivity to also simulate such a system with minimal with lesser number of interaction. And that's all. I am going to the second part of my talk, is that how to understand the dynamical behavior of such a system. I'll just introduce very briefly the dynamical quantum phase transition and how the usual markers of dynamical quantum phase transition, usual markers of dynamical phase transition fail in detecting these transition points. I'll describe more. Is that if you consider the ground state of the Hamiltonian belonging to corresponding to the parameters alpha 0 and h 0, and evolve it with the sudden quench-it with sudden quench is essentially change the parameters very suddenly to of the Hamiltonian from alpha 0 to h1 and h 0 to h1, and evolve the corresponding ground state with this Hamiltonian, you will end up with an evolved state that is looking like this. And what Marcus Hale has initially showed that if this alpha 0 and h 0 and alpha 1 and h1 belong, whether they belong to same or a different phase, could be inferred from the dynamical behavior of this evolved state. What it says is that the equilibrium properties of this model, alpha 0 and h 0, and whenever someone calls something a phase, it is in general an equilibrium property, that is a static property. What this says is that such a static property, which in general equilibrates at infinite time, and it takes a lot of effort to keep the system in equilibrium, such behavior could be studied using under dynamics, and this is what Hale has shown. But although I would like to mention a very serious caveat here, that this method has several flaws. People have shown counter arguments that there are several models that do not follow this logic. But in our case, the Ising class of Hamiltonians in general follow this property, and essentially what it can be seen is that how it can be seen is that we can use the markers of DQPT. Is that if you just look at the overlap of the evolved state with the initial state, and this is called the return probability or called the Loschmidt echo, and take the corresponding logarithm of it, and this we call it as the rate function. What happens is that if these two alpha 1 and h1 and alpha 0 and h 0 belong to the same phase, you can see that the Loschmidt echo will be non-zero, and the rate function in general is analytic. There is nothing weird about the rate function. On the other hand, if they belong to the different phase, alpha 0 and these two, if they belong to a different phase, the Loschmidt echo becomes 0. That is, the initial state and the evolved state becomes orthogonal to each other, and the corresponding rate function, because this is 0 and there is a logarithm that is sitting in front of it divided by the number of particles, the rate function becomes non-analytic. This is the main result of Marcus Hale, and it has especially he has observed in between the magnetic phases. I'll describe what they are. Our model, the model which I have shown before, has a dispersion relation that is looking like this. That is the energy relation in the momentum basis. Energy relation in the momentum basis, and the corresponding real and imaginary parts of JR. That is this JR is again 1 over R power alpha. What is it's not important to understand this equation that much, but what is important is that this thing, the dispersion relation, goes to 0 at k equal to 0 when h equal to 2. Okay, that is the first important observation. That is, whenever you are quenching, this is a phase diagram. From 0 to 2, the system is in a ferromagnetically ordered phase. When 2 and above, it is in the disordered phase, or more or less a paramagnetic phase. I don't want to call it ferromagnetic and paramagnetic because we have not formally calculated the order parameters, but just ordered and disordered. Now, if you observe that if I quench from the ordered phase from 0.5 to 1.5, the lighter green, sorry, R of t has a very smooth behavior, but whenever it crosses the critical point and quenches with respect to 2.5, it has a very sharp peak, and at these points, the model is non-analytical. On the other hand, if I start from 0.5, it does not matter which alpha it is in, alpha 0.5 or 1.5, this behavior is quite universal. In that 0.5 to 1.5, again, there is a very smooth behavior, and 0.5 to 2.5, there is sharp peaks that are coming up. What is important to see here is that these non-analyticities are periodically are uniformly spaced, and there is only one such time. On the other hand, in the non-local phase, there is there are two different uniformly spaced non-analytic behaviors that are present. This is the first observation of DQPT in the magnetic phases. This is not that important in the sense what we are after.
Ganesh, so we have 5 more minutes.
Yeah, I'm almost done. Yeah, thank you. So what we are after is that the transitions in alpha. So if you remember, the alpha is the decay rate, and the corresponding decay rate also follows the same phase, which I have shown you in the first slide, is that it undergoes from non-local to quasi-local to local. What we are after is that if I quench a non-local ground state corresponding to, with respect to a Hamiltonian that is present in the quasi-local or local phase, can I detect these transition points? That is the significance of the paper. In that, we'll do the normal Loschmidt rate. So if I start from 0.5, it will look at these points, and if I go from 0.5 to 3, there are transition points. But what happens is that if I go from quasi-local to local, although I am crossing a transition point, Loschmidt echo cannot detect this alpha equal to 2 point. So what this graph is essentially showing is that if you quench from 0.5 to here and 0.5 to here, it behaves exactly the same. There is no stark difference between the dynamical behavior of the rate function, and it does not signify that you have crossed a critical point. What we can use is we apply an information theoretic approach. That is, we deploy mutual information to calculate, to see the behavior that in this phase from H and alpha plane, if you quench from directly from this non-local phase to quasi-local and local phase, you can observe that mutual information behaves in certain way. And in order to detect this point, alpha equal to 2 point, we deploy something called fine grain analysis, and we show that mutual information follows a different law when quenched between these two phase regimes. I'll just quickly show that we calculate the two-party density matrix now, this time with respect to time, and it becomes even more harder to calculate these elements, because if you remember, in statics it was just this block, but in dynamics there are much more number of terms, and we have to deploy something called a Pfaffian. Thankfully, the corresponding studies are done in these two. Thankfully, there is an algorithm that has been prescribed by Michael Wimmer from TU Delft, who has shown that these Pfaffians can be calculated. Quite easily. Now, the final result is that mutual information follows different fall-off rate when quenched from, if you observe here, if I quench from 0.5 to 0.5 to 0.8, that is in the same phase, it follows a very small fall off rate. That is, it is quite stable. On the other hand, as you have crossed the first transition point, 0.5 to 1.5 and 0.5 to 3, it behaves like this. And you can see that it does not matter in which magnetic phase you are in, 0.5 or 2.5, these remain unchanged. In the same phase, it is quite stable, 0.5. And when you cross the transition point of alpha equal to 1, you can see that the fall off rate is quite drastic. Again, this did not serve our purpose. We want to detect the alpha equal to 2 transition point. Now, this is where fine graining comes in, is that rather than fixing to the transition point, rather than fixing to the transition point with the same hedge, consider the same hedge, and you will see that the fall off rate will be different when you're quenching from hedge to more precisely. If you are quenching from here to here, that is 6 and alpha, and if you are quenching from hedge order to disorder, you will see that the fall off rate goes like this. And if you see from if you are quenching in the same phase, the fall off rate looks like this. Whenever you are quenching in the same magnetic phase for the same alpha, it follows such a fall off rate, and as opposed to while crossing the phase boundary. This transition is only observed when you cross alpha equal to 2 point. That's it. We summarize. So the LRI model is useful to present many experimental platforms, and recently, as I've shown, trap diamond has been done more than 5-6 years ago, and superconducting is quite upcoming. And right now, last night there was a very important result. And static entanglement properties of fully connected model can be mimicked using the finite range interaction, and the transitions in decay rate can be detected using mutual information as opposed to Loschmidt echo. That's all. Thank you.
Okay. Thank you, Ganesh, for this nice talk. So now it's open for questions.
Thank you for your talk. I have one question.
Yes.
What is Parfanian correlations for correlations as compared to simple correlations?
Yeah. Okay. So. Okay. So I can go to the paper. So this is we have written it in the appendix. Let me just quickly answer you. Is my paper is visible, right?
Yes, I can see, but you
Yeah.
can tell. Okay.
Yeah. So here, when these correlations in general are whenever there is no dynamics, it is just a function of it is just a determinant that is based on this block. That is just that are functions that are calculated by G. On the other hand, whenever you want to calculate in dynamics, this is no more the ground state is the state is not just a ground state of a nice Hermitian Hamiltonian. Rather, there is an e power minus IHT. It induces many other properties that should be calculated using the Pfaffian. When it is starting, we just have to calculate the determinant. When under dynamics, you have to calculate the Pfaffian. We have to construct a skew-symmetric matrix of using this and find the corresponding Pfaffian for this.
Thank you.
Any other questions? If there is no other question, then we can move on to our next speaker.
Thank you. I'm stopping.
Ganesh, can you please?
Yeah.
Yeah, sure. Yeah. Thank you.
Thank you.
Okay, so our next speaker is Dr. Shorodip Sasmal. So I know him from quite a lot of time. So he was also a postdoc when I was doing PhD at NIT Patna. So let me formally introduce him. So he has done his PhD from Bose Institute, Kolkata, and then he moved on for a postdoc at RRI, then at NIT Patna, and now currently he is affiliated to IIT Hyderabad. So his research interest is like quantum foundation, quantum information, and certification of randomness, steering, these things. So Soroj is done, so you can present your today's talk.
Yeah, thank you, Sumit, and thank you, the organizer, for giving me a chance to present my work at this very dynamic conference. So let me. Acha, it is showing host disabled participant screen sharing.
Okay, okay. Let me make it first. Yeah, now you can share your.
Yeah. Yeah, so I hope I am audible and my screen is now
Yeah, absolutely.
properly shared.
It's visible.
Okay.
Yeah.
Okay, so today I'll be talking about.
You can make it full screen. It's full screen, right?
Now it is full screen. Yeah,
Okay.
So today I will be talking about self-testing of multiple copies of maximally entangled state and mutually unbiased basis. That means in a lucid way, the anti-commuting measurements. So basically, what is self-testing, that I will first introduce, and then why it is difficult to self-test multiple copies of maximally entangled state, because a single copy of maximally entangled state has been self-tested, and nowadays it is very simple to do. But multiple copies, there are many problems with it. So I will talk about that. So this work is basically done with my current group leader, Dr. Alok Pan, and Prabhuddha. And Prabhuddha is right now doing his postdoc at IISER Behrampur, and Alok is associate professor at IIT Hyderabad. So what is self-testing? So self-testing means let's say I have a black box. Black box means I don't know the inner working of the device, or the user may not know the inner working of the device. But what I can do with the black box is that, let's say there is a input switch in a black box that I can press some button, and let's say there is some light bulb attached to it. So whenever I press a button, the light bulb will glow. Let's say there are two possible light bulbs are there, red and blue. And in the simplest case, let's say there are two possible input, let's say switch 1 and switch 2. Now what I can do using this black box, I can collect the statistics. That means the input output statistics, that whether switch 1 corresponds to blue bulb or switch 2 corresponds to red bulb. That kind of way I can collect the probability of obtaining certain outcome when some input is given to the box. Now the spirit of the self-testing is that I have to certify what is happening inside the black box only from the output statistics. So at first, listening to it, it may be look as that it is not possible. But thanks to quantum correlation, we will prove that it is indeed possible, that by looking only into the statistics, we can actually characterize the inner working of the device. So in a more formal way, one can define that this set of probability distribution is called behavior. And if it is a quantum device, then that behavior must be produced from the Bond rule probability distribution. That means in this device, there is a quantum state that is a density operator. And by giving input means I am measuring some POVM onto the state. So by using the Bond rule, we can actually calculate this set of joint probability. But we will show that only looking into the statistics, we can actually certify what is going on inside this black box. Now, why would do it? Because in a present day, quantum correlation has very significant applications in in a wide range of information processing tasks such as key rate generation, random number generation, or maybe one-to-many key conference, and those kind of protocol needs absolute security. That means the user can't rely the devices they are using. So they need to have a self-testing protocol to conclude that their device is working properly. So apart from the information processing task, self-testing also provides the foundational insights into the geometry of the quantum set. That means how the quantum boundary looks like, because in a geometrical view, we don't know what kind of principles are there to characterize the quantum boundary. So self-testing provides a way to characterize extremal quantum correlation and then the quantum boundary. I will briefly talk about what is quantum extremal correlations and why they are very important in the security of device independent information processing task and all that. And also in some part in the delegated quantum computing, where user writes a program and send to a quantum cloud, and then the quantum cloud solves that program and then again send the solution to the user. But the problem is how user knows that these solutions are correct. So self-testing protocol provides that kind of safety to user device. Now I have already formally defined self-testing in a single scenario. So I want to comment that for if the user has only one black box, then it is not possible to self-test a device. I mean, possible with some extent, but completely device independent way, we cannot do it. So for this, we need to have a two black box scenario, and two black box scenario is very important in quantum information regime also, because we all know in present days that there is Bell non-locality and all that, and this correlation playing a crucial role in quantum computing and information processing task and all that. So let's say we have two black box, and these two black boxes are space-like separated. That means the black box 1 cannot communicate with black box 2, and in the black box 1 there is input that is denoted by X, and for black box 2 the input is denoted by Y, and the corresponding outcomes are given in the picture. Now here the collected statistics are characterized by the behavior that is set up this joint conditional probability distribution. From now on, I will omit the term conditional part, that this is the joint probability distribution of these two black boxes. Now the formal definition is that up to local isometry. What is local isometry? That I will talk about. That up to local isometry, we can characterize this we can characterize this black box by only seeing this behavior. Now, how to do that? So there are two possibilities we can do. That is, let's say we collect the behavior and we define a Bell function, and if the Bell function of that behavior is the maximum achievable, if that Bell function on that behavior gives you the maximum achievable quantum value, then we can be certain that this behavior is unique. And by observing this, the quantum value of the Bell function, we can be sure of that one thing, that this behavior must be that P star behavior. And how can we observe? There are a lot of experiments going on to observe the Bell inequality. Bell function means is the simplest example is the CSSH inequality. Also, another way to self-test this particular behavior is to come up with a map which gives you that if this quantum state belongs to this Hilbert space and the measurements gives you some unique property with any other strategy, if you self-test this state and measurement, then also one can self-test this P star behavior. Today in this talk, I will explain that how maximum violation of a tailor-made Bell inequality gives us the power to self-test this unique behavior, and then correspondingly the measurement settings and the states involved. So this is just the usual EPR bomb scenario where two party let's say Alice and Bob are space-like separated and no communication is happening in between them. And Alice's measurement settings are X and Bob's Y, with the outcome represented by AB. Now, in quantum mechanics, this joint probability is characterized by the bond rule, that is the trace of rho and the measurement operator of Alice, tensor measurement operator of Bob. And also, let's say this behavior has some ontic model. That means this behavior can be generated by having a pre-shared strategy between Alice and Bob. Let's say that strategy is called lambda. Then this behavior in this strategy space, or sometimes we call it on the ontic space, is the factorizable. Under the assumption that Alice's settings does not affect Bob's outcome and Bob's measurement settings does not affect Alice's outcome. And another assumption is there, Alice's outcome does not affect Bob's outcome, and similarly vice versa. So it's called outcome independence. So from outcome independence and settings independence, which implies locality, gives you this behavior is actually factorizable in the ontic space. So now, it has been shown that John Bell first showed that whenever a behavior is factorizable in the ontic level, then one can construct an algebraic constraint on the ontic level, which can be measured in the operational level. That means in the lab. And one such and such constants are called Bell inequality. And one simple example is CH-SH inequality. That whenever the behavior is factorizable in the simplest scenario, that means if Alice has 2 measurement settings and Bob has 2 measurement settings with 2 outcome for each measurement setting, then in this 2-to-2 scenario, this CSSH expression gives a algebraic bound on the ontic space, which is 2, and historically it has been shown that quantum mechanics violates this bound 2 and can go up to 2√2. So basically the measurements operator are linear operators acting on the Hilbert space, and the quantum measurement is nothing but the implementation of a POVM. That means let's say it's a collection of positive semi-definite operator, and each operator is positive semi-definite, and some of the operators are called is equal to identity. So one can think of POVM as a decomposition of identity in various ways. Now, under what assumption we will comment that how, looking into the statistics, how can we be sure about that what was my behavior? So we assume that the experiment admits a quantum description because it is right now it's the most correct theory, and no communication from Alice to Bob. This is very important, because if Alice communicates with Bob, then even without quantum correlation, quantum mechanics can violate Bell inequality without having the quantum correlation. So this assumption is it's not a kind of assumption, it's kind of requirement to do the test. And also the Alice's settings and Bob's settings, they chose the settings freely. That means, let's say if Alice has 2 possible measurements and Bob has 2 possible measurements, and at a run, Alice can choose only 1 measurement from those 2, and Bob also can do same thing. So that choice is free, because otherwise free and independent of all other systems in the experiment. Because it has been shown, if that choice is not free, then also without having any quantum correlation, quantum mechanics can violate Bell inequality. And also there is no memory involved in it. That means each run of the experiments are independent, because collecting statistics needs each run of the experiment should be independent. Otherwise, in our statistics, we have to tweak such a way so that we can characterize whether the memory is there or not. So it's a very different line of study. And also another important assumption is reproducibility of preparation procedure. That means at each run of the experiment, the source prepares the same states for both Alice and Bob, so that the collected statistics is valid. Now, I was talking about CSSH inequality. So that is the expression of CSSH inequality. You can see this is just an algebraic constant on the statistical space. So in the local ontic model, since the joint probabilities are factorizable, that means these expectation values are also factorizable. So it can be easily checked that, sorry, there will be a there should be a minus sign here. This should be a minus sign. So in the local ontic space, since these expectation values are factorizable, so it can be easily checked that this is basically nothing but I can write it like that. I can write it like that, and it can be easily checked that the maximum value of this quantity is 2, if I can write in this factorizable form. But it has been shown that the quantum value is 2√2, and this 2√2 can be achieved with a very particular state, that is a maximally entangled state, and with some measurements which satisfies the relation that Alice's measurement should be anti-commuting and Bob's measurement should be anti-commuting. That means Alice and Bob's measurement must form the MUB, mutually unbiased basis. And this conclusion we can say that is up to local isometry. That means we don't know whether the maximally entangled state is in this form, that means this 5+ form, or maybe the other maximally entangled state form. That means, let's say, for example, another state is like that. That we can't tell. And also, if the state is this, then the measurement directions are different than if the state was there. So, but what will always satisfy that the state is maximally entangled and the measurements of its constituent parties are anti-commuting. But we will not, we cannot, we will not actually know that in particular in which direction they have measured, because there exist infinitely many directions which satisfies this anti-commutation property, and also the definition of maximally entangled state. So this is, we call it up to local isometry. And also we don't know whether the state is more than 2 dimension or not. So the exact statement should be, whenever any observer got 2√2 from a Bell experiment, he can be sure about that at least one maximally entangled state is there and measurements are anti-commuting in direction. Now, if we look into that geometrical view, what we can learn that this is in a, I have already mentioned that in a ontic space, if it is local, that means if it satisfies settings independence and outcome independence, then we call those probability distribution and local deterministic probability distribution. It may not be deterministic, but let's say it's a local deterministic probability distribution. And it can be shown that in the simplest 2-2-2 scenario, there are basically 16 joint probability one can collect in lambda space, let's say, but only 8 of them are independent, because there are 4 normalization condition and 4 locality condition, that means or the no signaling condition. So this behavior is basically an 8-dimensional space, and this forms a polytope. Polytope means a convex closed compact and convex set having finite number of vertices. So these points are called vertices, and these points are called vertex, and the plane joining these 2 vertex is called a facet. So, and interestingly, this CSSH expression is a facet in a local polytope. So whenever, so this is where the CSSH plane, the Bell value is 2, I mean the CSSH value is 2, and when it becomes 2√2, it actually creates the tangent in the quantum probability distribution. Okay, the red mark denotes the quantum probability distribution, and the green mark denotes the no signaling distribution. That means it constitutes only the assumption of no signaling. No determinism is not there, and other thing is not there. So and in a no signaling distribution, the maximum value of CSSH distribution can be 4, but for quantum mechanics, it is 2√2. And that hyperplane creates a tangent to the quantum probability space, and this is called historically Cyrelson first showed this, so it's called Cyrelson point. Though Cyrelson's derivations was not dimension independent, later we have done the dimension independent calculations. And another, but CSSH expression can only self-test this particular point, because at any other point, if let's say if I draw a CSSH point here, it will cut to different point, and it will also give me, if I get CSSH value, let's say some delta, that means those behavior are there which are giving me this value delta. So we cannot self-test those kind of behavior from CSSH value less than 2√2. Only the maximum violation of a Bell inequality can give me the self-testing statement, because the maximum violation creates a tangent in the quantum probability space. So people have introduced different kind of Bell inequality, like this one, tilted Bell inequality. It is called tilted because you can clearly see that this Bell inequality becomes a little bit tilted. So this is one of Bell inequality, and when it violates maximally, it will create again a tangent point, and this point will give the self-testing statement.
Brother, we have 5 more minutes.
Okay. Once, yeah. One point I need, I also want to add, that is mixed state cannot be mixed state. Self-testing of mixed state is not possible, because all the behavior of corresponding to mixed state lies inside this quantum probability distribution. So that is not possible at first look, but we don't know. So what are the existing results? Let's just summarize, and then I will tell you what we have done. That maximally entangled 2-qubit state plus MUB, that means the measurements at Alice and Bob's part, has been self-tested, and also the robustness has been also shown, that up to what extent we can say, if we get a Bell value around 2√2, then what extent we can self-test those maximally entangled state and MUB. Also, pure non-maximally entangled state has been self-tested, and interestingly, self-testing of pure non-maximal entangled state with non-maximal violation of Hardy relation has been shown. It is very interesting, because what just I argued, that for self-testing you need maximum violation of a Bell inequality because of a tangent, but Hardy relations has some peculiarity. That's why it gives the self-testing in non-maximal violation. And also different kind of inequality has been introduced to self-test QIQT states and all that. Also, self-testing of many pair of maximally entangled state has been shown, but not the measurement. So in this work, we have actually generalized this result, that many copy of entangled qubit state gives self-testing. Now one can ask why CSSH is not giving me the maximal, the many copies self-testing, because I told you, even if the dimension of the system is greater than 4, then also the maximum violation is 2√2. So that means if you have 3 copy, 4 copy, or more copy, the violation will not change. So only looking into the CSS equal to 2√2, we cannot tell whether the state is a single copy or multiple copy. So that's why we have introduced a tailor-made Bell inequality. It just looks like complicated, and it's a little bit mathematics. And we have also calculated the local bound. Mind it, the calculation of local bound of a Bell inequality is not a simple problem. Actually, the quantum bound, evaluating a quantum bound seems a simple problem than the local bound. Whatever. So this Bell inequality we have argued that this Bell inequality has the power to self-test the multiple copies. And if you look closely into this Bell inequality, basically Alice has 2 to the power n-1 number of measurement settings, and Bob has n number of measurement settings. So if one can look closely, if I put n equal to 2, it basically corresponds to the CSSH. And if we put n equal to 3, it corresponds Jesus elegant Bell inequality. So basically, this class of inequality is the generalization of a CSSH class inequality. And since it deals with the n number of settings at one side, it actually has the power to self-test multiple copies of. Since due to shortage of time, I am not going into the detail, but we have derived using the SOS method, which is basically operator algebraic method, and we calculate the optimal quantum bound of this inequality by coming outside from the quantum set, not from the inside. Because if we want to calculate the optimal bound from the inside the quantum set, we have to take assumption on the dimension of the system and the state. But in our derivation, we have not assumed those kind of things. I'm not going into this difficult mathematics part right now. And just I'm going into the conclusion that whenever I will get the maximum violation of this inequality, that the maximum violation is what you obtained is 2 to the power n minus 1 root n, and one can simply see if I put n equal to 2, that means it reduces to sh inequality, and that value becomes 2 root 2, which is the value what Sirelson has derived. But in the Sirelson derivation, Sirelson assumed the dimension of the system. Here we have not assumed the dimension of the system. So we got some statement. So whenever we got this optimal value, the state rho and the measurement settings must satisfy some constant relation. And from there, and if you can see that, let's say xi tensor yi and xk tensor yk, this must be commuting. And for all I and k, and so that means, and parallelly, that the state must satisfy this condition, that trace of some observable tensor, observable rho should be 1 for all j. So that means if these two conditions are satisfied parallelly, I mean simultaneously, that means rho must be a common eigenstate of those observable for all j. That means rho must be a pure state. And since this is basically the expectation value of two observable, since this expectation value is the extremal one, that means it gives you the maximum value 1. That means this rho must be a maximal entangled state. So the description of rho must be looked like this. Now let us analyze more. Since while doing the derivation, that whenever we observe this optimal value 2 to the power n minus 1 root n, we saw that Bob's measurement setting should be anti-commuting, and there exists n number of mutually commuting observable in HDA tensor HDB. HDA is the Hilbert space associated with Alice's system, and similarly for HDB. And for Bob's n number of mutually anti-commuting observable should present in HDB, because Bob need n number of mutually anti-commuting observable to have the optimal violation of that Bell inequality. So that means, so now this n number of mutually anti-commuting observable actually fixes the local dimension, and existence of this n number of mutually commuting observable fixes the global dimension. So using this very nice result that in any m qubit Hilbert space contains at most 2 to the power m plus 1 MUB, and thus 2 to the power m plus 1 number of anti-commuting observable. Thus, in order to ensure n number of mutually anti-commuting observable at Bob's side, the Bob's Hilbert space must be this dimension. So in that way, we can actually fix the global dimension also. And since there is a very famous result by Brunner that 2 copy of maximally entangled state is basically equivalent to 1 copy of maximally entangled QIQT state. So in that way, we can say that certain number of copies has been self-tested to have the maximum violation. So here we have plotted the number of Bob's measurement settings and the minimum qubit Hilbert space dimension required to obtain the optimal violation. And we see that if Bob has n number of measurement settings, basically floor m by 2 number of copies can be self-tested. So the upshot is a tailor-made Bell multi-settings Bell inequality we have proposed, and then we have evaluated the local and quantum bound as well. And this obtaining the quantum bound is just like the NP hierarchy approach, but the NP hierarchy is a numerical task to solve it, and we have invoked the sum of square method to obtain the quantum bound. And from there, we got that multiple copies of maximal entangled 2-qubit state as well as mutually anti-commuting measurement on one party's side can be self-tested. Now, many things can be done from here. That recently power of POVM has been revealed in generating more randomness than that was earlier obtained using the projective. So certifying such POVM class in device independent way will be of much importance. Also, self-testing of multiple copies of pure non-maximal entangled state, whether we can propose a general class of tilted Bell inequality to have a multiple copies, because in some information processing tasks, there are some information processing tasks where it has been shown that pure non-maximal entangled state gives more advantage than the maximal one. Also, self-testing of multi-party states as well as measurement settings would be a very interesting thing to do, but it will be very difficult. And also towards the possibility of partial self-testing of class of mixed state, because I told you class of mixed state is not possible because they don't lie on the quantum extremal. But we can, but what extent we can self-test, that may be looked in, that can be looked into in future. So yeah, so that's all. Thank you.
Okay. Oh, okay. So nice message. Okay, so the participant can ask questions now to the speaker.
Hello, sir.
Yeah.
My question is regarding career guidance. Sir, what is the research environment at RRI? Is RRI working on quantum computer?
Quantum computer, that I don't know, but quantum information and foundation, they work on generally. Also, other than that, there are many topics they do. In quantum related, quantum foundation information, that kind of thing, I earlier involved with Professor Sinha's group. She is an experimentalist in this domain. So she do experiments, quantum cryptography, and that kind of, so the bridge between foundation and information, let's say.
Okay, sir. Thank you.
Okay, any other questions?
Can I ask a question?
Yeah, quick question can be asked.
Thank you for your talk. You are using PVOM.
POVM.
Yeah, POVM. And my question is, can we associate all the operators inside POVM, like in quantum mechanics, we use quite often coordinate and P. So my question is, can we associate all the PVM operators with some known operators in quantum mechanics?
Okay, so no, because unitary so no, because there are many operators that are not POVM. The definition of POVM is collection of positive semi-definite operator, and which, let's say I have AX is the positive semi-definite operator, so it should satisfy this, and this is equal to identity. So it is the quantum measurement process. If I want to measure any any state, actually I am implementing this operator onto the state, and then I will observe this outcome A, and this operator satisfies this. One example I can give you, that a special class of POVM is called PVM, that is projective value measure. Whenever this satisfies, that this square equal to this. So in that way, let's say identity plus sigma x by 2 and identity minus sigma x by 2. This is another POVM, it's a spin class POVM. So it actually gives me this is the measurement process when let's say a spin half particle is going through a magnetic field directed in a x-axis. So then the probability of obtaining plus outcome when that kind of measurement is done is given by the Bond rule, that is trace of the quantum state and the measurement, because I want to see the plus outcome, that is identity plus sigma x by 2. So
thank you.
Okay. So if there is no more questions, then we can move on to our next talk. Thank you, Sarojita, for this talk. You can unshare your screen.
Yeah, I have stuff. Okay, thank you.
Okay. You can stay online for next talks. So our next speaker is there. Arijit Mondal.
Hi.
Hello.
Yeah,
Yes.
am I audible?
Yeah, you're audible. So let me introduce you formally. So our next speaker is Mr. Arijit Mondal. So his affiliation is he's from IIT Madras, and his research interest is entanglement theory, quantum information. So today his title of the talk is improved refrigeration in the presence of non-Markovian spin environment.
No. I think you are
You have changed.
reading some. No. I have sent some different thing.
Okay. So various techniques of quantum
Yeah.
image representations, right? So you can just share your screen. So
Yeah. Sure.
okay.
Let me share my screen. Enter screen. Share. Okay. So are you able to see my slides?
Yes, absolutely. So you can make it full screen.
Yeah. Sure.
Okay.
So yeah. Good morning to all. First, thank you for the introduction, and thanks to organizer for and Professor Panigrai to give me this opportunity to present my work in this QIQT platform. So today I will talk about the quantum image representation and basically quantum image processing. So as you can see, the title of the talk is various techniques of quantum image representation. So this is a rough timeline of the subject, how it developed and when it starts to develop. So the first proposed algorithm is qubit lattice, which was proposed almost 2 decades ago. Then a lot of protocols for quantum image representation, quantum encryption, watermarking, and all these things were proposed, and the subject developed. And you can see that after 2010 it starts to develop exponentially, and very few of them are listed here. So the outline of my talk is like this. First, I will talk about the quantum image representation. What is the quantum image representation? Then I will classify the quantum image representation based on the type of representation. Then I will talk about a few of the algorithm like FRQI, NEQR, and QIRC. Then I will move to a recently proposed algorithm, hybrid phase-based representation of quantum images, which is HPPRQI. And finally, I will summarize my talk. So let's first start with what is quantum image representation. So quantum image representation is the representation of an image on a quantum state. So image consists of pixels, and the pixel has two parts. One is location information, and another is color information. So representing both this part or encoding both this part on a quantum state properly is the quantum image representation. Now a quantum state has three parts. Let's say this is a single qubit state. So the quantum state has three parts. One is the basis, another is the amplitudes, and third one is the phases. So generally the location information of the quantum images are represented in the basis, because there is a unique relation between the pixel coordinates and basis vectors. So that I will explain later. And the color information are represented either in the basis vectors or in the amplitude. So based on the type of the representation of the color image, the quantum image representation proposed protocols can be classified roughly into two sections. One is the amplitude pixel representation on amplitude, and another is the pixel representation on basis vectors. So few of the algorithms of each category are listed here. Now first I will talk about the amplitude based representation, and one famous algorithm under this category is FRQI, which was proposed in 2011. So this is the initial state for required for the FRQI images. So actually to represent a square image of dimension 2 power n cross 2 power n, you need 2n plus 1 qubits. Out of the 2n plus 1 qubits, 2n qubits are used to represent the location information, and 1 qubit is used to represent the color information. One additional qubit along with the amplitude of each basis are used to represent the color information. So this is the quantum operation that is applied to encode the color properly. So this is basically a control rotational gate where the location qubits are the control qubit and the additional qubit is the target qubit, and this is the final state which represents an FRQI image. And you can see that this additional qubit maintain the normalization of the state. Now one small example is shown here. So this is one, this figure is taken from this review article, and you can see that to represent the images in FRQI algorithm, so first you have to convert your pixel value, I mean the color values in to some angles, and these angles are used to represent the amplitude and to represent the color in the amplitude of the images, and this is the quantum state of a FRQI image. So now I will move to the basis vector based representations. One algorithm in this basis vector based representation is NAQR, which was proposed in 2013. So this is the initial state that is required for the that is required to represent the images using NAQR method. So to represent again to represent a square image of dimension 2 power n cross 2 power n, you need 2n plus q qubits, where q is the number of color qubits required to represent the image. Now this q will depend on the type of the color. Let's say if you consider the grayscale image, so you need 8 qubits, because 2 power 8 is 256, and grayscale image has 256 types of colors. So for square image of dimension 2 power n plus 2 power n, and the image for grayscale image, you need total 2n plus 8 qubits. So this is the quantum operation that is needed to represent the image. This is basically a multi-control NOT operation, where the control qubits are in the location, and the target qubit is the color qubit, and this is the final state for NAQR. Now again one small example is shown here, and this figure is adapted from this article. And here you can see that this is a grayscale image, and the grayscale value on each pixel is represented in 8-bit binary sequence, and equivalent quantum state is prepared. Equivalent quantum state of this string is prepared, and which is attached to the basis state, and finally this image is represented here. This is the quantum state for a NAQR image. Now I will move to the another image representation protocol under basis vector representation category. Here, instead of using a normal state, the images are represented on a class state. And again, the here to represent the images, a mixture of both computational basis and the diagonal basis are used. So the motivation behind using class state and the mixture of both computational and diagonal basis is, if you represent the cluster state in terms of both computational and diagonal basis, there is not a unique representation. There are a lot of possibilities which will be beneficial for in terms of security purpose and in terms of the reducing gate cost purpose. That I will not discuss in details today. So I will explain this algorithm briefly. So this is how the cluster state is prepared. So a control Z operation is performed in the adjacent qubits, and this is a typical 3-qubit cluster state, which is represented in terms of both computational basis and diagonal basis. Now this type of test states are used to represent the images in QIRC. This is the quantum operation that is performed, and this is basically a multi-control Z operation, where your control qubits are the location qubits and the color qubits are the target qubits, and this is the final state of the images of QIRC images. Now I will show you the one example. So this is initial cluster state, and this is the image that you want to represent. So to go from this to this, you need to use this quantum circuit. You can see that there are multi-control Z operations are performed, and using those operations we can represent you these images. So you can look at the histogram plot. So this is the histogram for the original cluster state, and this is the histogram for the image that you want to represent. So Now, what are the disadvantages of this algorithm? So there are few advantages. So in the amplitude based pixel representation algorithms, the main problem is the after every quantum operation you have to maintain the normalization of the state, which is a crucial property of a quantum state. So to maintain the normalization, you have to unnecessarily use some additional qubits. On the other hand, for basis vector based representations, there is a huge number of qubits and huge number of non-local gates are required to represent the image, which will prone to error. So let's see what is the possible remedy, I mean possible way to reduce these disadvantages. Till now we have represented our color information either in the amplitude or in the basis. Now there is one more part of a quantum image, which is the phase. Now let's see what will happen if we use the phase of a quantum state to represent the color of an image. So with this motivation, we prepared one algorithm. So before explaining the color part of the algorithm, let's first let me discuss the location information representation part. So this algorithm can represent a rectangular image of dimension h cross w. So to represent the height h, you need n1 number of qubits, and to represent the width w, you need n2 number of qubits, and you need one ceiling function and one log function to calculate the value of this n1 and n2. And if your h is less than 2 power n1, or if your w is less than 2 power n2, then the additional qubits are considered as redundancies. Now, I told you that there is a unique relation between the pixel coordinates and quantum basis. Now, how this relation can be established? Let's say this is one of the pixel coordinate h cross w. Now, this is a decimal number. This decimal number you can represent it in n1 digit binary string, and this decimal number also you can represent an n2 digit binary string. Now, the total binary string, you can make one equivalent quantum state of this binary string. So in this way, you can uniquely represented your location information to the basis vector. Now let's talk about the color information. So as I told you that we can represented the color information in phase. So to do this, one possible solution is you first change your color value to some angle using this formula. Here you can see we showed a small image, 2 cross 2 image. These are the pixel value 5, 170, 285, and these are the corresponding angle which can be obtained from this formula. Now one easiest thing is you use a control sorry, you use a control phase gate for each pixel, and you will exactly you are able to represent the pixel information in the phases. Now from this histogram plot, you can see that from this color code and from this bar plot and from these values, you can see that the pixel information can be exactly represented using this type of unitary operation. But the advantage of using this type of unitary is you are able to reduce the number of qubits, because FRQI needs 2n plus 1 qubits. Here you need 2n qubits. So 1 qubit you are able to reduce. But the problem is that still your non-local operations are there. So if you use this type of unitary, you are not able to reduce your non-local operation. So this can be modified a little bit, which will reduce your non-local operation. So you can see here that you can represent the same image. You can represent the same image using this unitary also. And here you need a little bit of algebra, because if you remove the control on this unitary, so let's say if you want to fix the phases of let's say 0 0 state, it will automatically changes the phases of 0 1 state, because there is no control on this unitary. So now when you want to fix the phases of 0 1 state, it will change the phases of 1 1 state. So you have to maintain, you have to keep the record, you have to keep this in mind, that it will modify the other pages, and accordingly you will maintain the page updation, and you can represent the images using a lesser number of non-local gates. So to keep this record properly, we propose a phase updation algorithm and phase updation formula that I will explain. So let's first let me explain step by step how this unitary will represent your color information on phase, and what is this formula. So let's first apply this unitary to represent the phases associated with the basis 00. So you will feed the original phase of let's say the original phase of 00 state, you can feed, and it will give you the, it will modify the phases of 00 state, but again it will I mean additionally it will change the phases of 01 state. And here the this value is so small that I think you are not able to distinguish between this and this color, but believe me, there will be a little change. But the thing is, if you want to represent the phases of 00 state, it will modify the phases of 01 state. Now you want to modify the phases of 01 state, then what you will do, you will subtract the phases of 00 state from the required phase of 01 state, and the subtracted phase you will feed to the circuit, and you will get the original phase of 01. So you, if you feed, let's say if you feed the you want 1.328 pi now, but you are feeding 1.289 pi. So if you feed this subtracted value, you will get here the exact value, which is 1.328 pi. This is 1.328 pi. And the thing is, when you are modifying this, it will changes automatically.
You have 5 more minutes.
Oh, sorry. Yeah, fine.
Okay.
Okay, so this is this will change this 1 state. Now let's go to step by step. You want to represent the 10 state, the phases of 10 state. Then you are nothing, I mean no subtraction is required because it will not affected by anything. So it will, you will feed the original phase to the circuit, and you will able to represent the phases of 10 state, but it will again change the 11. Now if you want to fix the 11 phase for 11 basis, you will apply a control phase operation, and you will subtract the effect of all previous operation from the required value of this for this 11 basis, and you will feed that subtracted value, and you are able to represent this image. Now with this motivation, we can generalize this image for any n cross n or any for any dimensional images, and where this unitary will be used as a master operation, and there will be some control on this master operation that I am showing you. So this is a rough workflow of this of our proposed algorithm. So our algorithm has three inputs. One is the location input. One is the I mean, first of all, our algorithm has two parts. It's a hybrid algorithm. We have one classical part and one quantum part. So in classical part, we have two inputs. One is the location information input, and one is the color information input. And in the quantum part, there is a number of qubits required, and the initial state is the input. Now in the first channel, it will read the location information, and it will split it into a binary string, and it will make some blocks and subblocks. Now what is the requirement of blocks and subblocks, and how it can be prepared, that I will explain in the next slide. But these block and subblocks are required for HPBRQ images, and after preparing this block and subblocks, this data will send to this channel. Now in this channel, first the phases, initial phases of the images are recorded. Then there will be a phase updation formula which will maintain the record, and which will maintain the phases that you need to feed to the circuit. Now after doing all the calculation, the final phases will be sent to the quantum channel, and in this channel the location information are represented on the basis, and next the color informations are represented on the pages, and finally it will be represented on a quantum computer. Now what is the nomenclature, what is the blocks and subblocks, and how the nomenclature can be done? So let's say you want to represent these images on the quantum state. Now you can see that you have zero, you have you have to represent, you have to make some blocks and subblocks depending on the number of ones in terms of n minus 2 qubits. in terms of the number of ones in the n-2 MSB, because the last two qubits are used to perform the master operation, and the n-2 MSB are used to perform the control operation. So let's say if here there is no one in the first 3 qubits, here is no one in the first 3 qubits, so the block number is 0. Here is only one solitary one in the first 3 qubits, so the block number is 1. Here there is 2 ones in the first 2 qubits, first n-2 qubits, so the block number is 2, and so on. So after doing this block division, you have to make some subblocks depending on the position of 1 in the n-2 MSB. So here the 1 is there in the first qubit, so the subblock is 1 1. Here the qubit is there in second qubit, 1 is there in the second qubit, so the subblock number is 1 2. So in this way the block and subblocks are prepared. Now for a 2 power n1 plus 2 power n2 image, there are total n-1 blocks, n is n1 plus n2, and 2 power n-2 subblocks. Now each sublocks has n-2 CRs. Each block has n-2 CR subblocks, and each subblocks has dimension 1 plus 4. Now the quantum operation is designed like this. So the control of the master operation will depend on the block and subblock number. For 0th block there is no control. For first block there is only one control. You can see here and here and here. From in second block there are 2 controls. You can see that here and here and here and so on. Now the position of the control will depend on the subscript of the subblock number. So let's say for 1 1 subblock, the control is on the first qubit. For 1 3 subblock, the control is on the third qubit, and so on. Now the thing is, when you will when you will fix the phases of block 0, it will definitely changes all the higher subblocks. So you have to maintain that. So to maintain that, we propose the phase updation algorithm. So let's say you want to fix the phases of 1 3 subblock. Now we have to subtract the effect of 0th block from the original phases of 1 3 subblock. Now when you fixing this, it will change the 2 2 3 2 1 3 and 2 1 3 subblock. So you have to maintain that record. So our algorithm will work like this. First it will read the pixel information, then it will prepare the blocks and subblocks. Now it will enter to the block in ascending order. Let's say from 0, then 1 block, then block 2, then block 3, and so on. Now after entering into 1 block, it will fix the phases of all subblocks, and it will keep the record that how it will change the higher subblocks. And in this part, one phase updation formula is applied, which will maintain all this thing, and which will give you the phases that you need to fit to the circuit. And this process will be repeated until you reach to the maximum block, and finally your image is represented on a quantum state or on a quantum computer. So this is the mathematical prescription of our phase updation algorithm. So basically the basic prescription is very simple. Every time you have to subtract your stored phase from the original phase, and the subtracted phase you have to feed to the circuit to get the original phase. So let's go step by step. So for block 0 there is nothing to do. For block 1 you have to subtract the effect of block 0. Let's say if you want to fix the phases of this subblock 1 and 2, which is like this, which will be like this, and you have to subtract the information of the 0th block from the phase information of the 1 1 1 and -2 block, and you have to feed the final value to the circuit to get the original phases. Now this is a generalized formula for first subblock for first block. And after completing the first block, the algorithm will move to the block 2. Now in block 2, if you want to, let's say if you want to represent the information for 2 K1 K2, let's say, so you have to subtract the information of 0th block, 1 K1 subblock, and 1 K2 subblock. So you have to subtract all this value and from the original pages, and the subtracted value you have to feed to the circuit to get your exact phase values. Now we can generalize this formula for any Rth block. So you can see the formula here. This K is nothing but a set of all possible ones in all possible situation, all possible positions, starting from 1 to, let's say, R-1 number of ones. So with this mathematical prescription, you can represent your HPBRQI images. Now, after representing the images, the next thing is how to measure the local phases. So let's say this is your HPBRQI images. Now we have to measure this phase. So to do this, first you can apply this type of measurement operator where one identity is there in the mth position. Now after doing this, after applying this measurement operator, you will get this state where one is ket0 in mth position and one ket1 is there in mth position. So the state is the superposition of these those state, and now you can apply one unitary on this state. After applying the unitary, finally you will get this state. Now after doing little bit of algebra, you will get the probability of getting ket0 in mth position is cos square phi pq by 2, and the probability of getting 1 in mth qubit is sin square phi pq by 2. Now if let's see, if you perform the n number of measurements, and out of the n number of measurements, n0 times you will get ket0, and n1 times you will get ket1. Now if you subtract these two values and you do little bit of algebra, finally you will come up with this equation. So now using this equation and providing the information of the global phase, you can measure the local phase corresponding to each basis. Now this is a representation of a complete 4x4 grayscale image is shown here. So this is the quantum circuit required to represent this image. Now from this to this plot and this image, you can see that the pixels are represented exactly on the phases of the quantum state. So this is the representation of HPBRQI images. Now what are the advantages of these images? So the first in terms of number of qubits. So the number of qubits used to represent the images by few protocols are listed here, and from here you can see that our HPBRQI image using the minimum number of qubit among all the protocols listed here to represent an image of size 2 power n plus 2 power n. And now let's the next thing is in terms of number of gates. As I already told you earlier that for basis vector representation method, it uses a huge number of non-local gates compared to the amplitude-based representation. Now I made a comparison between some amplitude-based representation algorithm with HPBRQI. Now we can see that our HPBRQI images will use the lesser number of qubits than the lesser number of gates than the other protocols. And another important thing is, if you go to the higher order of gate, your number of gate used will be reduced. But in the other algorithms, if you go to the higher order, go towards the higher order of the gate, the number of gates will used will be increased. So this is one of the great advantage of HPBRQI images. Now this is the summary slide. As I am running out of time, I was already warned, I am already warned, so I will not explain this slide. So yeah, thank you. So if you have any question, then I am available.
Thank you. So we can have a quick questions.
Yeah, sure.
Hello, sir.
Yeah.
Why we
Hello.
need quantum image?
Why you need quantum image?
Yes.
Hello. Yeah. There is a I mean lot of advantages in terms of your memory required to represent an image, and the encryption purpose and the watermarking purpose. There are a lot of advantages than the digital images.
Okay, sir. Thank you.
And thank you for your talk. I have one question.
Yes.
What is the meaning of cluster state? Is it tensor product of multi-parted state?
Okay. Let me go back to that slide. So the definition of the cluster state is like this. You just use the control Z gate between the adjacent qubits, and the state that will be obtained is the cluster state. Here.
So it is multi-parted state.
Yeah.
Thank you.
Okay. If there is no more questions, then we can go on to our next speaker. So thank you, Arijit.
Yeah,
Thank you for the talk.
let me switch off the sharing.
So
I don't know how to
next
switch off.
speaker. Okay. So our next speaker is Ms. Aparajita Bhattacharya. She's from HRI. She is doing her PhD from HRI. So her research interest is basically entanglement theory, quantum information. And today her title of the talk is Improved Refrigeration in the Presence of Non-Markovian Spin Environment. So welcome. You can share your screen.
Okay. So is my screen visible?
Yeah, yeah. Absolutely.
Okay. Sorry. So firstly, I'd like to thank the organizers for giving me this opportunity to present my work here. So the title of my talk is Improve Refrigeration in Presence of Non-Markovian Spin Environment. And this work has been done in collaboration with Ahuna Ghoshal and Professor Ujjwal Shen. So the very first paper regarding quantum refrigerator is this, which is by Popescu. And in that paper, they pose a very fundamental question that is there a fundamental limit to the size of quantum devices, like quantum thermal devices like refrigerators? So they want to study how small, what is the smallest possible thermal device which can act as a refrigerator. And so by size of a thermal device, they mean the dimension of the Hilbert space to which the system belongs. So, and along with that, the quantum thermal device also has to be self-contained. That is, it can work without an external source of energy. So the aim in their paper was to find a quantum thermal device which is of the smallest size, which can perform the refrigeration of a particular qubit, and also it has to be self-sustained. That is, it can work without an external driving energy. So this was the main aim in their paper. So in our paper, we have used the model taken in their paper. And so I'll just briefly discuss in the first part of my talk how the refrigeration actually occurs in that model, or what is the principle behind the cooling of the smallest possible refrigerator, quantum refrigerator. So suppose there are two qubits, qubit 1 and qubit 2. So, and the qubit 1 is the object to be cooled, and the qubit 2 is the qubit which helps in the refrigeration process. And this is the Hamiltonian of the system, E1 pi 1 plus E2 pi 2, where this pi I is 1 1. So the ground state energies of each of these qubits are 0, and the excited state energies are E1 and E2 respectively. These are the ground state and the excited state, and they consider the case where E2 is greater than E1. So and at the beginning, they considered that both the qubits, that the joint initial state of the system is in a tensor product of the thermal states of the individual qubits. So this rho 1 2 is tau 1 tensor tau 2 initially, and where this tau 1 and tau 2 are the thermal states of each of these qubits, and this thermal states tau I is given in this manner, and where this Ri is calculated using this partition function. So this is so now in this model they define the temperature of this of the two qubits in terms of the populations of the ground state energy level. So and their definition of temperature, this is the definition of temperature used in Popescu's paper. So their definition of temperature only holds for the states which are diagonal. And since they consider initially a thermal state, and they also consider only a, only a decohering channel. So there are no off-diagonal terms appearing in the density matrix after the evolution of the system. And so the total system is always in a diagonal form. And so for such a kind of system, they have defined the temperature in terms of the populations. So this is the thermal state of the ith qubit, which can be written as this in this manner: Ri00 plus 1 minus Ri11, where this and if we write this tau I in terms of the thermal states, then we can get this Ri as a function of this EIs, and this as this Ris and 1 minus Ris are the probability of finding the qubit in 0 and 1 respectively. So if we write this this density matrix in terms of the thermal state, then we can get this equation, and from this equation we know this Ris, and therefore by inverting this equation we can obtain the temperature of the two qubits Tr, a temperature of the ith qubit Tr in terms of the population of the energy level of the ground state energy level Ri. So this is how they define the temperature in their refrigerator model. So and another thing that here I forgot to mention, that both of these qubits initially were at a temperature Tr. Both of them were at the same temperature Tr. Okay. Now from this equation we can see that cooling of a qubit, cooling of qubit 1 implies higher ground state population of qubit 1. So they have defined the temperature in terms of the population, the ground state population of the qubit. And we can see from this equation that as the Tr decreases, the ground state population, that is Ri, increases. So basically we want to, what do we mean by the fact that we want to cool the qubit 1? So we want to increase the ground state population of qubit 1. That is how we ensured the refrigeration. Okay. So now what is the idea behind the cooling of the first qubit? So this is row 1, 2, that is the joint density matrix of the two qubits. And if we calculate this, then we will see that the probability of the eigenstate 01 is 1 minus R1 in times R2, and the probability of the eigenstate 10 is 1 minus R2 times R1. So this R1 is the ground state, is the probability of getting the ground state of the qubit 1 in the ground state, and this R2 is the probability of getting the ground state of qubit 2. So since they have considered E2 greater than E1 in this situation, if we calculate this probabilities in terms of these the thermal states, and from there we get the energy relation. So using that, we will see that 1 minus R1 times R2 is greater than 1 minus R2 times R1, which implies that this state is more favorable than this energy state. So 1,0 state is more favorable than the 0,1 state. So here, this is the 1,0 state, that is in this state, the first qubit, the ground state population is less than the excited state population of the first qubit. That is, the excited state population of the first qubit is larger. But we do not want that. We want the ground state population of the first qubit to be more in order to refrigerate this qubit. So what do we do next? So we apply a unitary operator U, which swaps the two energy levels 1,0 and 0,1. So from this state, we go to this state 0,1, where the ground state population of the first qubit is higher than the excited state. And so in this manner, there is a since the ground state population of the first qubit increases, there is a refrigeration of the first qubit and also a heating of the second qubit. So, but here is one point is to be noted, that since these two energy levels 1,0 and 0,1 that we saw previously, 1,0 and 0,1, these two energy levels are not degenerate, that is, they are of different energies, and the energy of this level 0,1 is higher than the energy of this level 1,0. So therefore, some external work, that is external source of energy, is to be required for this unitary operation. So since the energy of 0,1 is larger than that of 1,0, the some energy has to be supplied from outside in order to perform these swap operations. So this is 1 million. So this refrigerator is not self-contained. However, if we keep on repeating this unitary operation continuously, so gradually the 2 qubits 1 and 2 will reach the steady state temperature. This one will reach T1s, which is less than TR, and this will reach T2s, which is greater than TR. But here an external source of energy is required. So now we move on to the 3 qubit refrigerator, and we see that if what happens to the if we have 3 qubits, and can we construct a refrigerator which is self-contained in the 3 qubit regime. So the idea of this model is to replace the external work by a different source of free energy. And this free energy can be provided whenever a system has access to 2 thermal baths at different temperatures. So previously we had only 2 qubits, and both of those qubits were at the same temperature. But now we have another extra qubit, third qubit, and we say that the temperature of the third qubit is larger than the temperature of the other 2 qubits. So, and this temperature difference actually acts as effectively as a source of free energy. So this is accomplished by adding a third qubit in contact with a thermal bath at a hotter temperature T8 greater than TR, and this qubit plays the role of the engine. And thus our fridge consists of 3 qubits. The first one is the object to be cooled, second is a spiral, and third is the engine. So this is a final refrigerator model, and in this, so this is the object to be cooled, this is the spiral, and this is the engine. These two are at temperatures TR, and this is at temperature TH greater than TR. And we see that under this setup, if we consider this condition, that is E3 equals to E2 minus E1, then under this condition, the 2 energy levels of the system, which 010 and 101, become degenerate, and thus they can be swapped without any requirement of external energy, 101 and 010. So the swap from this level to this level. And once the state goes to this level, we see that this is 010, and therefore the ground state population of this qubit becomes higher. So in this way, the refrigeration occurs, and here no external source of energy is required. So how do we implement this conversion of 010 to 101? So we introduce an interaction Hamiltonian in the system, which is of this form, and we consider that the interaction is weak compared to the Hamiltonian, that is Hamiltonian parameters, that is EI, the energies of the qubits. EI is much greater than G, and in this regime, the interaction will not significantly alter the energy eigenvalues or eigenvectors of the system, governed by H0. So H0 was a local Hamiltonian, the local Hamiltonian of the system. And so we see that by using this interaction Hamiltonian, no external control is required because both these 2 energy levels become degenerate, and so they can be swapped without an external source of energy. Now, why do we keep this temperature TH greater than TR? This is because this actually helps in the biasing of the refrigerator that takes the qubit from 1 to 2. Actually, if we keep this TH greater than TR, from this equation we can see that it enhances the probability of the forward flip and diminish that of the backward flip. Because keeping TH greater than TR enhances the probability of the forward flip. So we get more and more states which are 010, and therefore it enhances the probability of cooling. So this is our final refrigerator setup, and this is the model that we have used in our paper. So this is the object to be cooled. These two acts as a refrigerator, and this is the spiral, this is the engine. And the first and the second qubit are kept at temperatures TR, that is room temperature, and the third qubit is kept at a slightly higher temperature than this. Okay. And the small sized quantum thermal machines are relevant to various fields. So these are the applications in biology. For example, if cooling of active site of a protein can be achieved, then increased catalysis rates may be possible, and in their quantum refrigerators may be useful. And second, also in nanotechnology, it benefits from cooling at atomic scale is there. So now in our paper, actually in Popescu's paper, they have considered a toy model dynamics. But since this toy model dynamics, these are not very relevant in realistic scenarios, what we consider Markovian and non-Markovian dynamics. So evolution under Markovian approximation, but we mainly focus on non-Markovianity. The works on Markovianity have been done previously. So we go from Markovian to non-Markovian dynamics. So evolution under Markovian approximation is a special case and hardly occurs in realistic scenarios. The Born-Markov assumptions have limitations on the environment such that the thermal baths may be infinitely large and should have a continuous energy spectrums. However, many environments do not follow this and are non-Markovian, for example, spin bath. So non-Markovian environments are more realistic, and because Markovianity is a very specific, Markovianity occurs under very restrictive conditions and under various specifications. And non-Markovianity is a more general and more realistic scenario. So if you move another step further, then that a further more realistic scenario would be mixed Markovian and non-Markovian environments. So there may be mixed local and non-Markovian environments. The subsystems of the machinery evolve under a combination of local Markovian and local non-Markovian dynamics. This is because some of the non-Markovian baths do not have Markovian limits, and so they cannot be considered Markovian under any limiting conditions. So there may be a mixture of Markovian and non-Markovian environments, which is more realistic. And these are, for example, found in hybrid systems like atom-photon models. So now let's see, what do we mean by non-Markovianity? So this is the basic idea behind a non-Markovian evolution. So for example, these green circles, this is my system, and this blue rectangle is my environment. So in a non-Markovian dynamics, the system continuously interacts with the environment, and there is there is an information flow in both ways. That is from the system to the environment and from the environment to the system. However, in the Markovian scenario, the system interacts with the environment for a small period of time, and after that interaction, after interacting for a small period of time, the system throws away the environment, and again it interacts with a fresh new set of environment. And this time is so small that we may assume that the environment, the information that flows from the system to the environment, that the environment forgets. So there is no information backflow from the environment to the system. So this is a particular very restrictive condition under which we consider Markovian dynamics. So there is no information backflow, and the system there is no information backflow from the environment to the system. So now we have considered, first we have considered the case where all the three baths attached to the three qubits are Markovian. And then what we have done, we have replaced one bath, one by one, we have replaced one bath by a non-Markovian bath. And finally, we have seen the effect when all the three baths are non-Markovian. So we replace the baths one by one, or replace the Markovian baths by a non-Markovian one, and see what is the effect. So the Markovian bath that we have considered is a bosonic Markovian bath, and this is the system bath interaction, where these etais are the bosonic creation and annihilation operators for the omega, for the mode omega, and for the ith qubit. And this is the non-Markovian bath that we consider. So this is essentially a spin star configuration. That is, at the center there is a spin, and surrounding the central spin there are a number of other spins which lie on the surface of an imaginary sphere surrounding the central spin. So this is the spin star interaction, and this is the bath Hamiltonian, and this is the system bath interaction Hamiltonian. So our model is a 3-qubit, 3-bath refrigerator model, and this is the system Hamiltonian. And when we consider the ideal case, that is all the 3 baths are Markovian, then we use this GKSL master equation to see the dynamics. And when we consider the mixed Markovian and non-Markovian evolutions, we use this modified master equation. So this is a modified master equation for mixed Markovian and non-Markovian dynamics. Here, this dm is a dissipative part for the Markovian dynamics, and this dnm is the dissipative part for the non-Markovian dynamics. And this Im denotes the ith Markovian path, and this In denotes the ith non-Markovian path. So, and this is our first result. That is in the ideal Markovian case, that is when all the 3 qubits are connected to 3 Markovian paths. So under this scenario, we see that yes, there are 3 situations which we name as S1, S2, and S3. So S1 is the case when there is only transient cooling and no steady state cooling. And S2 is the case where there is both transient cooling and steady state cooling, but transient cooling is better than steady state cooling. And S3 is the case where the steady state cooling is better than transient cooling. So we have obtained these 3 situations under different parameter regimes of the Markovian channel, of the Markovian paths, different parameter regimes. And under these parameter regimes, we divide our mixed Markovian and non-Markovian scenarios into 4 categories. So this is the case where so these are 4 cases: A1, A2, A3, and A4. This A1 corresponds to the case where the first qubit is non-Markovian and the other 2 are Markovian. And for example, this alpha 0 is the parameter of the non-Markovian path, and this alpha 2 and alpha 3, we take all possible combinations of S1, S2, and S3 to cover all the regimes. So the first path is non-Markovian and the other 2 paths are Markovian. Similarly, for the other cases also. For example, in this, the first 2 paths are Markovian and the third path is non-Markovian. And in this manner, we have 4 altered scenarios. These are, that is A1 where the first path is non-Markovian and the second and third are Markovian. A2 where the first and second are Markovian and the third is non-Markovian. So these are the cases where it is 1 non-Markovian path, and these 2 are the cases where there are 2 non-Markovian paths. That is, the first and the third are non-Markovian in A3 and the second and the third are non-Markovian in A4. So these are our 4 altered scenarios.
So Aparajita, we have 5 more minutes.
Yeah, okay. So so here we see when there is only 1 non-Markovian path connected and it is connected to the first qubit, that is the cold qubit. So then we see that there is effective cooling in the transient and steady state region, and also it is advantageous over the ideal case. However, when the non-Markovian path is connected to the third qubit, we see that there is no cooling in the steady state region and only a small transient cooling. Also, when we connect 2 non-Markovian paths, we see that when the non-Markovian path is connected to first and third qubits, there is effective cooling, and this is advantageous over the ideal case. Whereas when the non-Markovian paths are connected to 2 and 3 qubits, then there is no cooling and only there is no effective cooling. And also in this case, we see that the attainment of steady state is not guaranteed. But in the previous case, we saw that attainment of steady state is guaranteed. So what are our main results from this? We see that when the path connected to the first qubit is made non-Markovian, whatever be the nature of the other 2, then there is effective cooling and it is advantageous over the ideal case. But if we do not attach the first qubit to a non-Markovian path, that is the cold qubit to a non-Markovian path, and attach the other 2s with non-Markovian or Markovian whatever, then there will be no cooling. So in order to achieve cooling of effective cooling and effective cooling, we have to attach the first qubit with a non-Markovian path, whatever be the nature of the other 2. So these are the first results. Replacing the Markovian path attached to a cold qubit of a refrigerator with a non-Markovian reservoir results in a considerable lowering of the temperature of the cold qubit compared to the situation where all the 3 paths are Markovian. And this advantage is apparent both in the transient and steady states. However, connecting the other 2 qubits in non-Markovian paths while keeping the cold qubit in a Markovian reservoir does not provide advantage over the ideal scenario. And also for non-Markovian paths greater, the number of non-Markovian paths greater than 1, the steady state may be attained at very large times or may not be attained at all. So next, in order to understand what is the reason behind this advantage and how to explain this advantage, so we move on to define a quantifier of non-Markovianity. And since we are interested in the temperature of the cold qubit, that is, we are interested in the dynamics of the cold qubit, that is the first qubit, we trace out the other two qubits and we just look at the evolution of the first qubit. So let's say this is the local Hamiltonian of the first qubit. And considering this a few lines of algebra, it follows that we can define a quantifier of non-Markovianity in this manner, MC, which is given by this equation. And here there is an optimization over all Markovian channels lambda m, and this is the lambda c, that is a channel whose Markovianity or non-Markovianity we want to detect, that is lambda c. And for that channel lambda c, if MC is greater than 0, it will imply non-Markovianity, and if MC is less equal to 0, it will imply Markovianity. And we have also shown one example, not example, actually, it's an example, yeah. So we have compared this, our non-Markovianity measure with the well-known RHP measure, this reverse Fourier measure. And we see that, so this RHP measure is this GT. And when this GT is positive, it implies non-Markovianity, and our measure MC, when it is MC positive, it also implies non-Markovianity. So you see that in both the cases, similar to this measure can also detect the amount of non-Markovianity in the system. And this we have plotted for bath configuration A1. So next, finally, since noise is present everywhere, so presence of noise into the system is a further more realistic situation. So there may be mixed Markovian and non-Markovian environments, but the presence of noise along with non-Markovian environments is further more realistic. So we have also considered a case where in addition to the non-Markovian bath, there is a Markovian noise. So this is a system and it interacts with two Markovian baths and one non-Markovian bath. And along with the non-Markovian bath, there is some Markovian noise present in the system. I'll not discuss this in detail. I'll just briefly state the results. That is, we have considered these two noise models. So this is the system bath interaction for which one can derive the amplitude damping channel when the temperature goes to 0. But we have considered the system bath interaction for that channel, and we have not taken t equals to 0. We have considered the general case where t not equal to 0. So this is our first noise model, and the second noise model is this, for which one can obtain the generalized depolarizing channels and we have considered the system bath interaction corresponding to the generalized depolarizing channel as our second noise model. So these are the two noise models that we have used. And what are the results that we have obtained? That noise does not enhance the cooling over the ideal Markovian case, but the refrigeration still persists. And we have identified the range of the noise strength up to which the refrigeration still offers. So these are the results. And finally, I'll conclude my talk. So what are the main results of our paper? Firstly, we looked at situations where both transverse cooling and steady state cooling coexist in a quantum refrigerator system under ideal Markovian situation. Now, replacing the Markovian bath attached to the cold qubit of a refrigerator with a non-Markovian bath enhances the refrigeration compared to the ideal Markovian case. And connecting the other two baths with non-Markovian baths while keeping the cold qubit in a Markovian reservoir does not provide advantage over the ideal case. These are the main results. And then attainment of steady state is not guaranteed for number of non-Markovian baths greater than 1. And finally, in the process of explaining our results, we have also quantified, we gave a quantifier of non-Markovianity. And finally, we have obtained the range of additional Markovian noise strength for which the refrigeration still offers. That's all. Thank you.
Thank you, Aparajita, for this nice talk. So now it's open for questions. The participant can ask questions directly to the speaker.
Hello, ma'am.
Yeah.
Is there any concept of working substance as classical refrigerator here?
Sorry, what is your question? Working substance, you mean the working substance, you mean the first qubit?
So here we are treating the qubit as a working substance.
Yeah.
Okay.
Yeah. Yeah.
Okay, any other questions? So if there is no more questions, then we can move on to our next talk. So thanks, Aparajita, once again.
Thank you.
You can answer it.
Yeah.
Oh, it is already answered. So our next speaker, is he there? Okay, okay. Yes, come on. Okay, so our next speaker is Dr. Bialan Bhattacharya. He has done his PhD from SN Bose National Center for Basic Sciences, and currently he is affiliated with Indian Institute of Science Education and Research, Behrampur. He is doing his postdoc from there. So his research interest is quantum information theory and functional analysis. And today the title of his talk is Detecting Entanglement, Harnessing Lindbergh Structure. So welcome, Biolanda.
Thank you, Sumit. Am I audible?
Yeah, you're audible.
Okay.
So you can share your screen.
Thank you for your nice introduction, and let me share the screen. You just let me know whether it is visible or not.
Yeah, sure. Yeah, it's visible. You can make it full screen.
Full screen, yes. Is it okay?
Yeah, it's okay. You can start.
Okay, thank you. So I'd like to thank the organizers first for giving me the opportunity to present our work here. So the title suggests that today I'm going to talk on detecting entanglement, harnessing Lindblad structure. So I'll mainly talk about the positive maps and its applications. So without any further delay, let me tell you that this is based on our recent preprint, detecting entanglement. I've kept the actually title same as of our preprint. So detecting entanglement, harnessing Lindblad structure, and it's a joint work with Vaibhav Chimalgi, Sujatana Goswami, and Shamyadev Bhattacharya. It's an archive reference. So this is roughly the plan of my talk. First, I'll try to introduce the notions of positive maps. And mainly I'll concentrate on the positive maps between algebra of matrices. And I'll discuss something on decomposability and indecomposability of positive maps. And then I'll concentrate on positive maps on M2. M2 is basically the algebra of 2x2 complex matrices. And then I'll move to the application part, that detecting genuine multipartite entanglement using those maps. And then I'll discuss some measure on multipartite entanglement. Then I'll shift to the 3x3 algebra of 3x3 complex matrices and positive maps on them. And with that, I'll conclude. So the study of positive maps between sister algebra is one of the most active areas of research in abstract mathematics and in pure mathematics. But it started around with the work of Caddison, when he actually generalized the idea of Schwarz inequality. Now it is famously known as Caddison-Schwarz inequality. It originated, the idea of positive map originated from there. And later, William Steinspring introduced the notion of complete positive maps, which we usually, nowadays we use very much, the complete positive maps. And along with that, the several works by Arlene Stomer, Manduin Choi, S.L. Oranovich, and it actually got the shape that we have seen today. But eventually, mathematicians were interested in the studying positive maps on finite dimensional sister algebra, basically algebra of matrices. Actually, the thing is that the structure of positive maps, even in low dimensional algebra, is very complicated, because we wish to actually characterize what kind of structures do we have in the case of positive maps. Even in low dimension, it becomes a challenge. And here, actually, the notions of decomposability and non-decomposability or indecomposability comes into the picture. Historically, it was like that. mathematicians were actually, they knew that, okay, so positive maps geometrically forms a convex cone. And in that cone, complete positive maps and completely co-positive maps, I'll come to the definition later. These two are two known subcones of this positive. Now, it was a kind of thought that mathematicians used to say that, okay, whether a given positive map, can we write it is an algebraic sum of a CP map and a co-CP map? Because had it been so, our life would be very nice. So that is basically roughly the notion of decomposable. But unfortunately, or fortunately, because this actually led a huge, it led a huge research in this direction, that it was not true. And the famous paper of Mandu and Choi in 1975 came up with the first example of this indecomposable map. Now, a brief historical result. In 1963, Erling Stomer showed that if we consider positive map from M2 to M2, these all are decomposable, that we can always write it as an algebraic sum of a complete positive map and complete co-positive map. And in 1975, the first example of indecomposable map came into the picture by Mandu and Choi. It was a kind of twist in the whole theory. And in 1976, S.L. Oronovich showed that if we consider positive maps from M2 to M3 or other way around, M3 to M2 as well, then it is also decomposable. Now, these are pure mathematical ideas, but it also has got some nice applications in mathematical physics, namely in quantum information theory. So it does not only have the abstract mathematical beauty, it has got some application as well. And mainly, it's a famous paper by Hordeskis that they showed that actually a necessary and sufficient condition for entanglement detection, bipartite entanglement detection can be cast in terms of this positive map. And after this result, actually, I must say, a huge, initially it was kind of confined with the only mathematical community or mathematics community. But after this Hordeskis result, both mathematics and physics community came together to explore further that what kind of structures can we expect more in this structure of positive map, so that we want to learn about entanglement theory properly. So that is why this is one of the remarkable results. Apart from 1963 paper and 1976 and 1975, these three papers are also, are very important in the history of positive maps. Okay, so let me come to the definition. So throughout our discussion, we'll consider only the finite dimensional sister algebras. So for the time being, we consider that the algebra of D by D or complex matrices to be MD. So a linear map from MD1 to MD2, there's a D1 cross D1 complex matrices to D2 cross D2 complex matrices is said to be positive if it takes the positive semi-definite operators to the positive semi-definite operators. Or in other words, it preserves the positive cone. Now, if we say a positive map is K positive, if the amplified map, you see that there's a tensor algebra, actually MK tensor MD1 to MK tensor MD2. And the map is here IK. This is identity map on the ancilla system. Tensor the lambda original map. This is positive for some natural number K. And it is said to be completely positive if it is positive. This amplified map is positive for all K, for all natural numbers. Then we say that it is completely positive. Similarly, the map is called completely co-positive if the map concatenated with the transposition map, it's very famous, transposition map is also a positive map, that is completely positive. So this is a notion of complete co-positive. Now, one quick example, transposition, the very famous map, it is a positive map. It always takes a positive operator, positive semi-definite operator to a positive semi-definite operator. But this is not completely positive because we all know that how to detect the entanglement of Bell state that we usually learn in very first course in quantum information theory. We consider maximally entangled state in 2 qubit and we apply the transposition map on one part of it and we say that this is not a positive definite operator. So the state is entangled. So this is one example of a positive but not completely positive map, and which is actually essential to detect entanglement, bipartite entanglement. Okay, so one other important thing is that Choi-Yamelukowski isomorphism in this regard is given any positive linear map from MD to MD, there always exists a unique operator in the tensored algebra given by this prescription. This is, you see that this is a prescription of how to find this operator. This is a unique, we call it isomorphic image. The EI, EJ, I mean, these are the standard canonical base and standard basis of MD. We say that this operator is a unique operator that we find from a given linear map. So this is an isomorphism, and this isomorphism actually takes everything from the language of positive map to the language of operators. We call it, this is the famous Choi-Yamelokowski isomorphism. Now, in this regard, a map is completely positive if and only if its corresponding Choi operator is positive semi-definite. Actually, this Choi-Yamelokowski isomorphism translates everything from the language of positive map to the language of operators. Now, here the definition, the formal definition of decomposable map. A map, positive map lambda, is said to be decomposable if we can write in this form where lambda 1 and lambda 2 are complete positives. Otherwise, it is said to be indecomposable. Now, you may ask that, is there any example of such indecomposable map? Here is the first example that was given by Mandu and Choi in 1975. I mentioned earlier. It's very famous. It's now famously known as the Choi map. You see that this is a map from M3 to M3, 3 by 3 complex algebra to 3 by 3 complex algebra. And you see that you have to, I mean, we have to do some calculation to show that it takes all positive operators to the positive operators. And it's famously known as Choi map. Now, recently, we have introduced another positive map on M3 to M3, and this is given by this formula, this prescription, as you see. And we have been able to show that this map is also an indecomposable map. Actually, it detects some weaker form of entanglement, which is famously known as PPT entanglement or bound entanglement. Actually, this PPT entanglement is another important feature in entanglement theory, which is very hard to detect, because to detect PPT entanglement or bound entanglement, one has to deal with this indecomposable map. And there are few known examples of indecomposable map in the literature. And so this is what, okay, fine. Now let me concentrate on positive map of M2. Now, one may ask that why M2 is important here, because let me rephrase it properly, because okay, we can talk about positive map on M2 from the mathematical interest, that is fine. But if we go for the application part, I mean detecting entanglement, then we know that transposition is the only map is there that can detect entanglement in M2. And there is no one, because of the Stomer's result that any map is decomposable. So eventually, if you come up with a positive map, it will be decomposable. So transposition map is the only map there to detect entanglement. Now, still we are interested in the positive map of M2, not only from the mathematical interest, also from the application part, because we'll go for the multipartite case. Because in the multipartite case or in multipartite setup, the detecting entanglement through positive map is less explored, one kind of less explored area. So I'll come to this in the later part. So let me introduce. So in this work, we come up with this positive map. You see that these are the Pauli operators. Sigma is the Pauli operators. And it is, it has been written in some bad form, but in the compact form, this is, it's a bit nice. And you see that for gamma equal to half, so gamma is a parameter. You see that there is a single parameter gamma. It's a one parameter family. And you see that in the compact form, for gamma equal to half, you actually get back your transposition. So we say that this is a kind of one parameter generalization of transposition. Fine. So how to do, what to do with this map? Because okay, we get back transposition, and transposition is the only map to detect entanglement, bipartite entanglement, 2 qubit entanglement, to be very specific. But we'll explore the multipartite entanglement detection with this map. I'm coming to this. But before that, let me tell you that within this range, gamma from -half to half, this map is a positive map and not completely positive. So it is useful in detecting entanglement. So a bit multipartite entanglement. So we have I think you are, some of you at least are familiar with or many of you are familiar with the multipartite entanglement. So suppose we have an n-partite system and we consider sorry, am I audible? Hello.
Some noise is coming.
Okay. Some noise is coming. That's why.
Yes, agree.
Okay. So a joint state or an inpartite state is said to be fully separable if we can write it as a convex mixture of the tensor product states, where TIs are the state is biseparable if it can be written is is this kind of combination where entanglement may be present in inside A or A bar, but it can be written in this form. And if it is not, then we say that the sigma is genuinely entangled, genuine multipartite entangled. Now, detecting genuine multipartite entanglement using positive map was the first kind of research in this direction was initiated by this paper by Marcus Hubbard and Ritopurto Sengupta in this PRL 2014. And after that, the Cleavers, Huber, Lamy, and Murta, they actually came up with this paper in JMP 2017. They came up with the idea of lifting of suppose we take this lambda. We consider this lambda, which is from M2 to M2. We consider a new map, lambda tilde, which is given by this. You see that lambda A is acting on the A subsystem, where B and C subsystem, it is doing nothing. Basically, the identity is being acted on that. Similarly, when A identity is acting on A and C, on B, we are acting lambda B, and similarly for the C. And there is a last term, there is a C is a tuning parameter, which has been kept intentionally. I'll discuss why. So this is called the lifting of the map. And basically, what we show, actually, we want to show that it can detect genuine multipartite entanglement. So for any biseparable state, it should not evolve or it should not give us any non-negative non-positive eigenvalue. So that is why C, the parameter C has been kept for the tuning parameter. So for a given map, we can choose C in such a way so that for any biseparable state, it gives a it gives a greater or equal to eigenvalues. So it can detect genuine multipartite entanglement. So some numerics are there. We have shown that this W state, this is a genuine multipartite entangled state. This can be detected by this map for this range, this gamma range. Okay, and we also consider the noisy version of the W state as well, and we show that this also can be detected. The noisy W state, the genuine multipartite entanglement noisy W state can also be detected for this range. For P strictly greater than 0.73, it can be detected. And if we choose map in this domain, minus 2 by 5 to 2 by 5, there's no genuine entanglement can be detected by this gamma tilde. In this case, W class. And for gamma equal to half and gamma equal to minus half, this is a kind of base choice for the noisy W state. Okay, so this is a multipartite entanglement detection, genuine multipartite entanglement detection via positive map. Now, we have been motivated with this lifting, and we have been able to introduce a genuine multipartite entanglement measure, and which you find very much similar to the negativity measure entanglement. This is a kind of similar definition where kappa is a normalization factor, and we have been able to show that for any biseparable state, this measure will give us the 0 value. And it is monotone under local operation and classical communication, and it is a convex measure as well. Now we move to the positive map on M3. That is a kind of last part of our discussion. And our idea is to construct a new positive map. Whether we can construct this new positive map, and our idea was that can we construct from the Lindblad structure. Lindblad structure, you have in the previous talk as well, you have heard about the Lindblad form is very it's very important in the study of non-Markovianity or Markovianity of the dynamics of open quantum system, but it also has got a nice mathematical structure. So if we go back a little, I'm sorry I forgot to tell you that this is also kind of motivated from the Lindblad structure. So the idea is coming from the same way, but we are just playing with the dimension actually. So in M3, we consider the Gell-Mann matrices. In M2, we consider the Pauli matrices. Here we consider the Gell-Mann matrices, and keeping in mind that G1 is a 3x3 identity matrix, we construct this map where L is given by this. This is the Lindblad structure, Lindblad form that you have come across in several times. So this is a map, this is a prescription that we have seen, but this map is very interesting. In what sense? So if we put, because this is a parameterization, you see that there are parameters involved because gamma is at the parameters. Now we can choose this parameterization. We take gamma 2, gamma 5, gamma 7 to be alpha, some alpha, and gamma 3, gamma 6, gamma 8 to be minus alpha, and gamma 9 to be alpha by 3. And which, if we put that, we see that this phi alpha, depending upon also one parameter family of map, it takes this form. This what you are seeing in this presentation. And this for alpha 0, between alpha 0 and half, this map is positive, and alpha equal to half again gives me the transposition map. It's a 3x3 transposition map. So again, this is a kind of one parameter generalization of transposition on M3, just like we did in one parameter generalization of transposition map in M2. So it's a one parameter generalization of transposition map in M3. Well, but as we expect that transposition map is decomposable, this is also the case. I mean, we can show that we can split, or we can write this phi alpha as a form 1 minus 2 alpha identity. Identity map is obviously completely positive, and 2 alpha times transposition concatenated with ID. So this is a decomposable map. Just like transposition is decomposable, this one parameter generalization of transposition that we have obtained from the Lindblad structure, keeping in the Gell-Mann matrices in the Lindblad operator, this is again a decomposable map in this range 0 to alpha, 0 to half. But if we take a kind of different parameterization, we choose all gamma 2, gamma 3, gamma 4, gamma 5, 6, 7, 8, all kappa, and gamma 9 to be kappa by 3. Then we find that this is again a positive map within this range, kappa varying from 0 to 1 by 4. And this map is not completely positive for kappa greater than 3 by 16, but positive but not completely positive in 3 by 16 to 1 by 4. This is the thing. And now, interesting fact is that if we choose kappa to be 1 by 4, then we have been able to reproduce the Choi map, the famous Choi map. So we see that it is a kind of a family which at some parameterization giving me one famous map transposition, and some other parameterization, it is giving me another famous map, Choi map. So it is a kind of, I mean, this is generalized structure from which we can come up with the transposition, from which we can come up with the Choi map. But this Choi map is not indecomposable, but this Choi map is, if you see it little carefully, you see that this map is not same as what I introduced here. This. So there is a twist in the prescription. So that the Choi map that we have obtained up to now, that is decomposable. That is not the first Choi. I mean, the first example was given by Mandu and Choi, is not the map same as that example. But we have to do something to get back the original Choi map. Let me show you that. So this is a decomposable Choi map, or this is Choi map, some variant of Choi map, but which is decomposable. But we can play with the Lindblad operators. Those are in our hand. We can play with the Lindblad operators. These are the some operators you can see. There's a rank 1 projections. So with this prescription, we have been able to reproduce the non-decomposable Choi map. That is the famous Choi map that we obtained. So from the same family, we play with the parameters, we play with the operators, Lindblad operators, we come up with the famous positive map. So this can be, this can be a way to construct a new examples of positive map. And this also connects the various known positive maps. So let me conclude. So we have constructed a work parameter family of positive maps on M2, and this construction is motivated from the Lindblad structure, which is very important in the study of the dynamics of quantum system. And this class of positive maps, with this class of positive map, we have discussed the detection of genuine multipartite entanglement. We take forward the works by Huber et al. And we have proposed a measure of genuine multipartite entanglement by lifting the transposition map, which is very much similar to the negativity measure of the bipartite entanglement. And finally, we have also constructed the family of positive maps on M3 from the Lindblad structure, from which we get both transposition and two variation of Choi map. One is decomposable, one is indecomposable. So in some sense, the transposition and Choi map, both are famous maps theory, but they have some connection, maybe. It is worth to explore further. So they are connected by this relation in some sense. We can have by different parameterization, we can come up with two different famous maps. So with that, thank you very much for your attention. I'm done with my presentation.
Okay, thank you, Biolanda, for this nice talk. So now it's open for questions.
Thank you.
Participant can ask questions.
I have one question.
Yes.
Could you go to the previous slide?
Yes.
So question is, what kind of operator is mapped to the detection of multipartite entanglement? So, what kind of physical operator, like coordinate or like momentum? So what is the operator here? We need to measure the value of the operator. We need to measure to identify this detection.
Yes. Actually, the thing is that here, first of all, let me clarify. We are trying to detect entanglement via positive map, not operators. Okay. So the thing is that, okay, by operators as well, we can detect entanglement, but that is basically the entanglement witness. We call entanglement witness. Entanglement witness are basically Hermitian operators, which actually gives rise to the non-negative expectation value on all separable states, and it provides a negative, result if we take the expectation negative to some entangled state. So it is a kind of Hermitian operator. So if we wish to detect entanglement via operator, then we have to go up, we have to consider the approach of entanglement witness, and obviously these two are connected because any positive map which is not completely positive gives rise to some entanglement, and it can be used to detect it. So in general, it's a Hermitian operator.
Thank you.
No, well.
Okay, so any other questions? So if no, then let's again thanks the speaker.
Thank you, Sunil.
Okay. So this is the end of this session, morning session. So again, we will come back at 3 p.m. with after the lunch. Okay. Thank you.